Hey, hi everyone. Welcome back to my YouTube channel. My name is Sunny and I'm back with another exciting and important video. So guys, from this video onwards, we're gonna start the fine tuning of the large language model. As you know, I started one end-to-end LLM fine tuning playlist where I uploaded 13th video so far. In the last video, I discussed about the LLM quantization. And apart from that, I discuss each and every fundamental concept of the fine tuning. Now it's time to deep dive into the LLM fine tuning. I will show you the practical with respect to each and every framework. So today I'm going to start with the Hugging Face ecosystem. In the next video, you will find out axolotl, then unslot, the Llama factory, and you will find out fine tuning of different model, not only the text model, even I will fine tune the multi-model which can handle the images and other different type of data. So guys, if you haven't checked with this particular series, please go and check. And if you want to start this fine tuning, then you can start from this particular playlist itself. Now apart from that, I have uploaded so many other thing on my YouTube channel. If you are new to my channel, then please go and check inside this video section, or else inside this playlist section you will find out different video of the different concept. If you want to start your generative AI journey, then you can start from this particular playlist. Now guys, let's begin with the LLM fine tuning. First of all, I will tell you the agenda, that what all thing we are going to discuss, okay, and then step by step, one by one, we'll understand along with the example, and then we'll go with the practical. So guys, here I will show you the fine tuning of the LLM in that way only, like they have fine tuned the GPT model. So we'll take any raw model, we'll understand about the non-instructional fine tuning, then we'll understand about the instruction fine tuning, then we'll go with the preference alignment. Okay, each and everything step by step we'll try to discuss. We'll fine tune on top of the PDF data, on top of the TXT file. We are not going to fine tune directly on the instruction and the responses, means on the input and the output. No, not like that. I will go step by step. I'll pick up one model. I will basically first fine tune it on a domain specific data. Okay, the data can reside anywhere, right? In PDF, text, PPT, docs, anywhere, right? And after that only will come to the instruction fine tuning on a same model, and then we'll go with the preference alignment. Okay, so this video, this 3 to 4 video upcoming videos also is going to be very important. And yeah, so if you haven't subscribed my YouTube channel, please subscribe the YouTube channel and start your generative AI journey. Now let's start with the fine tuning of the large language model, guys. So guys, before starting with the LLM fine tuning, we'll have to understand the training pipeline of the large language model. So first, we'll take a walkthrough of the LLM training pipeline along with the example, and then only I will come to the fine tuning. Okay, the practical and all. So guys, if we're talking about the LLM, so we can choose any LLM. Let's suppose if I am showing you the fine tuning with the Llama, you can choose any other LLM. Okay, the code base would be similar. You just need to change the model ID. Okay, or from wherever we are going to pick the model, you just need to pick the any other model, any other different model. Okay, according to your requirement. Now guys, so if we're talking about the LLM training pipeline, so there is 3 stages. The very first stage is called the unsupervised pre-training. Unsupervised pre-training. Now this is also called self-supervised learning. Okay, self-supervised learning. Now the second stage is called SFT. Okay, this is very much important. SFT. Now what's the full form of this SFT? It is called supervised fine tuning. Okay, now if we're talking about the supervised fine tuning, so on a data level, on a parameter level, we can divide into two parts. The first is called, so let me write over here, on parameter level. Okay, so on parameter level, we can divide into two parts. The first is called full fine tuning. Okay, and the second is called partial fine tuning. Second is called, guys, let me write over here, partial fine tuning. So we're talking about the full fine tuning. Now here we are going to train all the parameter. Okay, so if we are talking about this full fine tuning, so we are going to train all the parameter. Now if we're talking about the parameter, guys, so parameter is nothing, it is weight and the biases. Okay, now guys, whenever we're talking about the full fine tuning, so this full fine tuning, okay, full supervised fine tuning, it is required more memory. Okay, it's required huge GPU memory. Okay, and it's required multi GPU setup also. Multi GPU setup if the data is very huge. Okay, if the data is very huge, if the model is very huge, in that case it will be required the multi GPU setup. So we avoid this full fine tuning. Now the second technique is called the partial fine tuning. Okay, so let's understand about it. So we're talking about the partial fine tuning. So again, there is two method. Okay, two method of it. So one is old school method. Old school method. Now inside this old school method, what we are doing, so we are just going to be freeze all layer and train last output layer. Okay, train last output layer. Now the second one, what we can do now here, freeze some starting layer, and retrain. Okay, so here it's not train, it's a retrain. Okay, now here is also retrain some last layer. Okay, so this a particular technique generally we followed in the CNN based architecture, right? CNN based model, or in a early stage LLM also. So in the early stage LLM, like, let me write over here, early stage LLM like bot. Okay, bot T5, right? T5 or BART. So this was the early stage LLM. So inside these particular model, we have followed this technique, right? But in a large language model, whatever large language model we are seeing. See guys, now one more thing. If I'm saying large language model, now what does it mean? So large language model means the model which was built on top of the transformer. Okay, so all the large language model are following this transformer architecture in backend. Okay, if you don't know about the transformer, guys, soon I will create one video on top of it, and for sure you will understand. Now guys, the second technique, okay, which is not an old school technique, which is a latest technique, so that is called, let me write over here, PEFT. Okay, PEFT, P-E-F-T. Now what does it mean? PEFT means, PEFT is called parameter efficient fine tuning. Okay, parameter efficient fine tuning. Now inside this parameter efficient fine tuning, we are not going to be train all the parameter of the model. Instead of that, we are going to be train some specific parameter, right? So let me write couple of techniques name over here, and in the future we'll discuss in a detail. Now guys, let me write one very popular name under this PEFT, which is called LoRA. Okay, I think you heard about this LoRA, right? So we have one quantized version of the LoRA. If we are going to be use the quantized model, so which is that is called QLoRA. Okay, now this Q is representing to the quantization. Okay, this Q is representing to the quantization. Now why we do the quantization, what we do in the quantization, you can check out with my previous video. So let me highlight some points over here. So in the quantized model, we use the lower precision model. Now what is the lower precision? Okay, each and everything I shown inside that particular video in the previous video, you can check out over there. Now this quantized model is a memory efficient model. Okay, so using this quantized model, we can do the memory efficient loading. Okay, so quantized model is the lowest precision model. If it is a lower precision model, then we can simply load into the memory. Okay, we can do the memory efficient loading and all. So that's a benefit of the quantized model. So LoRA is one of the technique. Okay, and if we can extend, right, if we are going to be use the quantized model, so that is called the QLoRA. Now if we're talking about the PEFT, guys, okay, so this PEFT, right, this parameter efficient fine tuning, this might work on a single GPU as well, right? So here I can write this PEFT technique, this might work with single GPU and smaller VRAM. Okay, now guys, this LoRA is not one and only the technique. Okay, we have some other technique also. So let me write the name of those specific technique, right, which I found apart from this LoRA, and definitely in this fine tuning series we are going to discuss that. So the second technique, which is called DORA. Okay, I'll come to this DORA. Maybe many of you hear this name first time. The second technique is called, sorry, the third technique is called the adapter. Okay, adapter layers. So adapter layers is also inspired from the LoRA only. We are going to be append some layer, okay, in the existing block of the transformer. Okay, so which is called the adapter layer. So DORA and the adapter layer is also a couple of techniques, okay, which we can use instead of the LoRA. Now we have some other technique. So let me write the fourth name over here, which is called the bitfit. Okay, bitfit. So this is also parameter efficient fine tuning, and it is getting very popular, and I'll show you the research paper of it. Now the fifth technique, which is IA3. Okay, I'll show you what is this IA3. This is also parameter efficient fine tuning. Now apart from that, let me write a couple of more names. So prefix tuning, it's also one more technique. For sure I'll show you this also. Okay, then the next is prompt tuning. Okay, prompt tuning. Prompt tuning, it might not be a part of the PEFT, but yeah, I kept it over here, and I'll show you the use of this prompt tuning as well. But guys, this LoRA is not one and only PEFT technique, which is parameter efficient fine tuning, where we are not going to be training the entire parameter of the model. Parameter means what? Weights and biases. Okay, instead of that, we are going to train only couple of parameter, only subset of parameters. So LoRA, DORA, adapter layers, bitfit, IA3, prefix tuning, these are some technique, these are some PEFT technique, and for sure in our fine tuning playlist we are going to discuss all these technique. Okay, now let me show you the research paper of it. So if you're talking about the IA3, so guys, here you can see the very good block on this IA3 over the Hugging Face itself. So the full form of this IA3 is infused adapter by inhibiting and amplifying inner activation. So the name seems very complicated, guys, but yeah, we can implement it by program, by the code and all, and that will not be very difficult. So it is a part of the LoRa itself. To improve the LoRa, actually we use this IA3, and it is a part of the PEFT. So that's why I kept under the PEFT itself, because we are using it to improve the LoRa itself. Yes, for sure, LoRa is very important, and the base for everything is the LoRa, LoRA. Okay. Now here, guys, you can see the research paper of it. You can check out the research paper. Even I'll show you that when I will discuss it. This is specifically this IA3 and all. Now here is a bitfit, guys. See, this is the research paper of the bitfit, simple parameter efficient fine tuning for the transform based mass language model. Okay, so we can use this bitfit also. Again, this is not very popular, but yeah, we can look into it. If you are doing some experiment, you can go through with it. Otherwise you can do everything from the LoRa, from the IA3, from the DORA, and the this one, basically one more is there. Let me show you. So here is a DORA, guys, right? So what is the full form of the DORA? Weight decomposition low rank adaptation, right? So this is the form of the LoRa itself. Now here again, it's a LoRa, low rank adaptation for the large language model, right? So let me highlight the points now. Let me summarize all the things. If we're talking about the partial fine tuning, we are just taking subset of the parameter. Let me mention over here, subset of the parameter. Okay, subset of all parameter. Okay, so these are a couple of technique. First is LoRa. If we are taking quantized model over there, then it's called QLoRA. Then DORA, then adapter layers. Yes, this was the technique, adapter layer. Bitfit, we can avoid this as well, but yeah, IA3 we can pick up this. Prefix tuning, it is also important. Okay, I'll come to this, I'll show you that. Prompt tuning is also again one of the technique. Okay, now this was based on the parameter, on a parameter level. Now guys, if we're talking about on a data level, so let me talk about the data level as well, and for sure I'll discuss that. Okay, so here I'm going to write on data level, on data level. So on data level, guys, we can divide into two parts based on the data preparation. If I'm saying data level means what? Based on the data preparation. Okay, data preparation. The first is called non-instruction fine tuning. Okay, non-instructional fine tuning, and the second is called instructional fine tuning, right? So maybe you heard this term many times, instructional fine tuning, but I think you were not aware about this instructional fine tuning. Now again, this is a part of the SFT, right? So if we're talking about the SFT, right, so this is very, very, very important, guys, right? So we can divide into two parts. First, on parameter level, again inside the parameter level, full fine tuning, where we required huge memory and the multi GPU setup, so generally we avoid it. Second is called the partial fine tuning. Again, we can divide into two methods. One is the old school method, where we are going to be freeze the layer and then we are going to be train the rest of the layer, and then we have an advanced technique, okay, which is called the PEFT. Now under the PEFT, guys, you will find out the LoRa, DORA, adapter layers, bitfit, IA3, prefix tuning, prompt tuning. Now guys, on a data level also, whenever we are going to prepare the data, right, for the fine tuning, for the supervised fine tuning, so again we can divide into the two part. First is a non-instructional fine tuning, and the second is the instruction fine tuning. So this is all about the SFT, right? Now the third term, which is called alignment with the human feedback, okay, or which is also called the preference based learning. So let me do one thing, let me cut this thing from here. This is also, I will show you, this is an example of the unsupervised learning and all. I'll show you that. First of all, let me keep it over here, this entire thing. Okay, and let me write about the RLHF. So guys, the third stage, which is called preference based, okay, alignment with the with the human feedback, right? Feedback. This is also called the preference based learning. Preference based learning. Okay, now guys, here what we are doing, we are aligning the response. Okay, we are doing alignment of the responses. Now this responses, actually this particular responses is being generated from the LLM. Okay, so guys, if we're talking about this preference based learning, so there was two methods. The first is called the RLHF. Now this RLHF, the full form of this RLHF is reinforcement learning through the human feedback. Now this particular technique was based on this algorithm PPO. Now what is the full form of the PPO? Preference, proximal preference optimization. Okay, proximal preference optimization. Now this particular technique, guys, okay, this PPO actually, it comes under the reinforcement learning. Okay, so that's why this is called RLHF, which was used by the OpenAI. Okay, which was used by the OpenAI for the preference based learning, right? I hope now you got it. Now the second is the popular technique, right? Now we all are using that, and even I will show you the practical of it. That is called the DPO. Now what is the full form of the DPO? The full form of the DPO is direct preference optimization. Okay, direct preference optimization. Now here, guys, this is supervised learning. This is supervised learning. I'll show you the data set of it. So in the data set you will find out question, then you will find out the response. Okay, and then you will find out the feedback of the response, whether the response is positive, whether it is negative, something like this. Okay, so guys, this is the complete stage of the LLM training pipeline. So first is called the unsupervised pre-training. Now the second is called the SFT, supervised fine tuning, and I explained the complete supervised fine tuning graph, which is very much important for us. And the third one, okay, after training the model, after generating a response, now based on that response, again we are going to be train our model, right? That is called preference based learning, or that is also called the alignment of the responses, the LLM generated responses. Okay, now let's see a couple of examples. So here I kept the example of the pre-training, what is the objective of it, what kind of data we are using. Then I kept for the normal fine tuning, that I kept for the instruction fine tuning for the RLHF and all, and what kind of technique you can use. And here I kept one more like example, okay, which is LLM wise Llama, GPT, Mistral. Okay, the name of the LLMs basically. So first, what was the name when it was unsupervised pre-train, then while the supervised fine tuning, then after the preference based alignment and all, right? So all the example I kept. Now let's take a look onto this. So first let's start with the pre-training, which is also called self-supervised learning. Now guys, this pre-training is also called the unsupervised pre-training or self-supervised learning. Now why it is called the unsupervised pre-training? Because in the data actually we don't have a label. And why it is called the self-supervised learning? Because the label is being created automatically. Okay, the next word itself will be the label, okay, in the data. So guys, what is the source of the data whenever we are doing this unsupervised pre-training? Now see, whatever model you are seeing, whether it's a Llama, Mistral, GPT, DeepSeek, cloud-based model like Sonnet, Opus, okay, Gemini. So these all the model initially have been trained on a very huge amount of data. Okay, now this data could be from the documentation, it could be from the research paper, this could be the common crawl data from the internet, okay, Wikipedia, encyclopedia data, books, okay, like different books, not even in English, even in the different other languages, right? Now guys, because of that, right, so see, initially actually we have to train our model on a very huge amount of data. As I given you the example of the different model, they all did this kind of training. Now this training itself is a bottleneck means because every country, every company not having this much of data, first of all, right? Now for training, okay, for training our model, if I'm saying model means transformer based model, for training the transformer based model on a very huge amount of data, we required a very huge infrastructure, huge GPU infrastructure, huge memory processor, right? So that is very money consuming and the time consuming thing. Okay, every country, every company cannot afford it. That's why many of the companies are not able to train their own specific large language model. You can see Grok, again it's from the USA, okay, Meta again from the USA, DeepSeek from the China, right? 90% model from the US itself, and it is being trained by those companies which is already having the access of the entire internet data, right? So this stage is an initial stage. Now why this stage is required? Because using this unsupervised pre-training or self-supervised learning, we can teach our model general knowledge. We can teach our model how it can understand the language, okay, the grammar of that language. So to develop the learning of the model, okay, to develop the core intelligence of the model, this particular stage is required. Now what is the objective? If we are talking about the technical objective, so the technical objective is next token prediction. This is called the language modeling. Okay, we are doing it on a huge amount of data, on a large scale of data. Because of this language modeling is called the large language modeling. This LLM word actually it came from here itself. Getting my point, guys, right? Now guys, here what you will get after this particular training, what you will get a base model actually, right? For example, Llama base, Mistral base, GPT base, DeepSeek, Gemini, right? Now if you want to, if you want a model which can do the conversation like a human, so again you will have to do the fine tuning, the instruction fine tuning, which is the next step that comes under SFT. Okay, if you want to make your model chat enable, right, so for that you'll have to do the instruction fine tuning, right? And if you want to align your model to the based on the human feedback, then you will have to follow the third step, which is called the DPO, okay, direct preference optimization. You will have to align the responses of the you will have to align the response of the LLM based on the human preference. Getting my point, right? So guys, here if we want to perform the pre-training, so we required this we required the data from the huge sources, okay. In short, I can say the data from the internet itself. What is the objective of it? To predict the next token, okay. This is called the language modeling. We are doing it on a huge amount of data, which is called the large language modeling, okay. The LLM word came from here itself. Now what is the result of it? The result, basically you will get a base model, okay. For example, Llama base, Mistral base, GPT base, DeepSeek base, Gemini base and all. I'll give you more example, don't worry. Even I can show you over the Hugging Face itself. So if you will go with the Hugging Face and if you will check with this Meta repository, so here you will find out a different model. Now see, this particular model is a base model, okay, Llama 213B. Now on the other hand, if you will see this model, okay, Llama 7B chat. See, this model is not a base model because after performing the pre-training, again this model have been fine-tuned for the chatting, right? Now I can show you the other model. So if you will check with the Llama repository, just go with the first page. Now here check. So Meta Llama 38B instruct, right? So this model is not a base model because this model actually have been pre-trained and then it is being trained on some instruction, right? So this is also not a base model. Now likewise you can check the different model. So which is a base one, which is not a base. In the name itself you will get it. See, this model is a base model. Now why this is a base model? Because the Llama 3.18p, it has not been trained further for any instruction, for any chatting kind of stuff. Okay, so I hope you got the meaning of the base model, right? Now why we are doing it? So that we can develop the core understanding of the model in terms of the language, in terms of the grammar. Okay, we can develop the general knowledge of the model. But guys, after doing this pre-training, still my model lacks to follow the instruction, to maintain the specific tone, in whatever tone basically we want to be train our model to produce the structure answer and all. Okay, so for that only what we do, we perform the supervised fine tuning. Now if we are doing supervised fine tuning, guys, so as I told you, we can divide into two parts. The first is called the normal fine tuning, this one, and the second is called the instruction fine tuning. Okay, instruction fine tuning. Now when we do the instruction fine tuning, so whenever we want to convert our model into the assistant, okay, whenever we want to convert our model into the chatbot, means it can do the chats like a human. Okay, it can do the conversation. In that case we do the instruction fine tuning, right? Now let's say we got the we have trained our data on a huge amount of data. We got a base model, right? So what we do, guys, we do the non instruction fine tuning, which is also called the normal fine tuning, right? And the second is the instruction fine tuning. Okay guys, if we're talking about the ChatGPT, so ChatGPT have skipped this particular stage. This normal fine tuning means domain specific fine tuning, domain adoption fine tuning. What they have done, they have trained their model on a very huge amount of data for developing a general knowledge, and for making it enable like a human conversation. Okay, they did the instruction fine tuning. Now they have done the instruction fine tuning on what? They have done the instruction fine tuning, okay, on the Reddit data, on the QLoRA data, Stack Overflow data, GitHub issues, right? Open forum, community forum, right? Where we have like question and answer, right? On top of that data, they have fine-tuned the model. Okay, they have fine-tuned the model. Now guys, when this normal fine-tuning means non-instructional fine-tuning is required, I can give you the example of it. So let's understand it over here. So let's say you have trained one model. Okay, I can take example of the Llama. Let's say you have trained one model, Llama model. So this model is a base model. Okay, I think you got to know what is a base model. Now guys, this particular model you want to train for your own domain. Let's say this is a base model. Okay, now guys, this particular model you want to train for your domain. Let's say your domain is a pharma, one pharma company, right? Let's say Sun Pharma want to train their own model. Okay, so they are not going to be train it from scratch. Okay, this pharma company, let's say Sun Pharma, they are not going to be trained from scratch. Okay, SCRATCH, right? They're not going to be trained it from scratch. What they are doing, they're just going to be take a base model. Okay, let's say Llama 13B. Okay, they are taking this particular model. They are going to be trained for the pharma domain. So they have a domain specific data. Domain is specific data. Okay, now on this domain specific data, again they will train which model? Llama 13B model. Getting my point, guys? So this particular training, see, this domain specific data, let's say this is available in PDF. Now if we're talking about the instruction fine tuning, so in the instruction fine tuning, the data will be available in a question and answer format. So we would be having question and answer, or you can say input and output format, or you can say like in the instruction and response format. Okay, in any of these format the data will be available. But Here the data is available in PDF. Let's say the data is available in TXT file. The data is available in any other file, okay, in any other file format. So what we'll do, so here we are not doing instruction fine tuning. Instead of that, we are picking up this data, this PDF data, TXT data, or data in any other format. This is a plain text. Okay. Now from this data itself, what we'll do, again, we'll train our base model. Okay. On top of which data? On top of this plain data. Now how the data is being prepared, I will show you that. Okay, from this plain data, I will again, what I will do, I will train my base model. And now this base model, right, Llama 13B model, this will be my domain specific model. Domain specific model. Domain specific model. Okay, now if I want to fine tune this model further for the conversation, okay, or for generating a text, the structured text and all, then I can do the instruction fine tuning. Okay, now why we can do the instruction fine tuning, why we are doing it? So that we can generate the structure output. Okay, so let's say we are asking some question to this llama, right? So it needs to be generate the answer, but here it know the domain specific knowledge, but still it is lacking to generate the structure answer. Okay, it is generating answer, but we want to be more refined. We want a specific answer with respect to this specific question. So what I'll do, I will perform the instruction fine tuning where I would be having the data in such a way. Okay, in which way? In question and answer format, in input and output format, in instruction and the response format. I'll show you the example. With that, your understanding will be more clear. So guys, that's what I was saying. If we are talking about the supervised fine tuning, we can divide into the two parts. One, see, we have a base model. Let's say this is my base model. So we have a domain specific data. Okay, that is a plain text in PDF, TXT, or any other file format. We can take that and again we can train our model. Now this model this model have been trained on a non-instructional data, okay, which is the plain text or something, right? Now what is the aim? What is the aim? Why we are doing it? Why we are training this model over here? So that we can basically give the domain specific knowledge to my model. Now further, if I want to generate a structure output, then what I will do, I will train my model on the question and answer data. This particular data for the domain itself, this particular data will have to prepare by myself. Okay, for the domain, ChatGPT took the Reddit data, QLoRA data, open forum data and all. But if you are in the specific, or if we are doing it for the specific organization, so this particular data will have to create by ourselves, right? And then further, what I will do after the instruction fine tuning, I will do the preference based tuning, okay, which is also called DPO or RLHF. Okay, human feedback, right? Human retraining based on the human feedback. Okay, preference based tuning or preference based alignment, anything you can say, and DPO is a technique of it, so that my model will be aligned properly in whatever way the end user want the output. I hope you are getting the entire chronology now. Okay, so guys, here you can see, if we're talking about the don't worry, I'll show the example and all. If we're talking about the non-normal fine tuning, okay, this is for what? This is for the domain adaptation, right? Now dataset, what? Dataset could be the plain text, okay, it could be the company document. Now use case, making LLM domain expert, okay, in any sort of a area like medical, legal, finance, e-commerce, whatever. Now what is the goal of it? To improve the model understanding and knowledge with respect to any domain, okay, or to adapt that particular language. Now what is the output style? Produce text continuously, not necessarily capable or following an instruction. Means if we are asking any question, for sure it's going to be generated text, but that text would be aligned with my question, would be the structure one. It might not be, because here again we are developing a knowledge, the domain specific knowledge of the model. Okay, meaning the model learning is the statistical distribution of the text, not question answering behavior. So again, we are not going to be train our model for such question answer. We are going to be develop the domain specific knowledge of the model. Okay, and I'll show you this thing practically. So what is the example? So example, let's say this is the text. Okay, how the data set will look like. So I kept like one paragraph over here. So Sunny Savita here, where AI meets unstoppable passion. Okay, this is where, not here. Where AI meet unstoppable passion, turning code, creativity, and courage into the legacy, teaching thousand to master AI one video at a time. Not just a creator, mentor, visionary, and a job maker. Don't chase opportunity, build them. Right. So this is the like a small text which I written. Right. Now over here you can see how the data will be created. Right. For this non-instructional fine tuning. Non-instructional fine tuning. Okay, so let's suppose this particular data you got from any PDF, right? So let's suppose you got this particular data from any PDF. Now how the data will be created for the non-instructional fine tuning, right? Non-instructional fine tuning. Now see, Sunny would be there, so Savita would be the output. Sunny Savita will be the input. Now this particular character will be the output. You can clean the data. See, later on I clean the data, so that's why this character is not there. Sunny Savita would be there, then where would be the output? Sunny Savita, where will be the input? AI will be the output. Sunny Savita, where will be the input? Meets will be the output. Sunny Savita, where AI meet, so this is the output. Sunny Savita, where AI meets unstoppable, so passion will be the output. Sunny Savita, where AI meets unstoppable passion, right? So this turning will be the output. Now guys, here you can see how we are preparing a data. So we are preparing a data in such a way so that we can predict the next token. Okay, next token means we got a model, okay, base model. Now let's say if I want to be train this base model on our own data, on our own text data, this text data in a PDF, this text data belong to any specific domain, right? So what I'll do, I'll prepare my data in such a way, in this particular way. Now guys, what is this? This data actually, it is representing to the self-supervised training only, self-supervised learning only. Okay, we have performed the unsupervised pre-training. Let's say I got one general knowledge based model. Now if I want to be trained for my own industry specific data, I can follow this step, and this is called the non-instructional fine-tuning. The data could be available in a PDF. We can get a text, we can again retrain the model, and we'll be getting a domain specific model, right? I hope this is clear. I'll show you with the practical, this entire thing, even the instruction fine tuning and the RLHF, means the DPO technique, okay, on the same model guys, right? Now let's see the instruction fine tuning. So guys, in the instruction fine tuning, right, which is again part of the SFT itself, so dataset follow instruction in the response format. Okay, don't worry, I'll show you that how it looks like, because I kept each and every type of data, right? From the Hugging Face itself, I kept the several data. So non-instructional fine-tune data, then instruction fine-tune data set, then preference alignment tuning data set. So this data set I just kept to show you how the data could be look like. Okay, the instruction fine-tune data and the normal data, and then the preference alignment data. Now here, so the data set follow instruction in the response format. What is the use case? The use case to build a chatbot, because the chatbot we required the model which can do the human conversation, human-like conversational. Okay, so for building a chatbot, or I can say for building the conversational AI, we always require the instruction fine-tuning on top of the LLM. So let's say we have a base LLM. Now this base LLM for performing the conversational, for building a conversational AI or to build a chatbot, what we'll do the instruction fine tuning. This is pretty much important. Now in between, even though we are again training this base model on some domain specific data with some domain, with this this base LLM on some domain specific data with the non-instructional fine-tune, okay, with the non-instructional fine-tuning data, right? But if I want to convert my model into chatbot, in the conversational AI, into the QA system, right, that definitely we require this instruction fine tuning. Now goal to teach the model to the human based instruction, right? Human like conversation. Now output style, so direct, helpful, and structure answer. More reasoning based answer. ChatGPT is the best example of it. They did the instruction fine tuning of the base model. They didn't did the they did the unsupervised pre-training on a very huge amount of data. They taught the model to the general knowledge and all, and then they perform the instruction fine tuning. But this stage is for us, for you and me, for a specific company, guys. Okay, if I want to avoid this particular step, okay, if I don't want to train my base LLM, if I want to pick my base LLM, if I want to do the domain specific tuning, so this step is for me. And if I want to convert my model, okay, into the conversational model, then this particular stage is required anyhow. Now what is the data example? So see, this is the data example which I mentioned. So here would be the instruction example, what mitochondria does in one sentence. Now see, mitochondria generate energy for the cell through the respiration. Okay, so we asked the question in this for this specific answer, and it has generated this specific answer, right? If I don't want to generate any extra thing, any other thing, that's why this particular fine tuning is required, right? Now meaning the model learns produce direct question answer, okay, and it learns how to generate the structure answer based on the given instruction, based on the given question. Now common data set, so these are the common data set which you can see over the Hugging Face itself. I'll show you in some time. Now how ChatGPT have performed the instruction fine tuning, on which data they have done. So they have done on the Reddit conversation, on the QLoRA, on the Stack Overflow conversation, Stack Exchange conversation, right? GitHub issues discussion, right? Open forum and the community board like Hugging Face, Kaggle. I'm just saying with respect to the coding as of now, but yeah, it could be any open forum, community forum and all. Okay, so like the in the comment itself we are doing a discussion with respect to any specific post, right? So that data also could be possible, right? So ChatGPT, the OpenAI picked this particular data for the instruction fine tuning of the ChatGPT model, of the GPT model, which have been used under the ChatGPT application. Okay, now guys, what is a combo? Means if we are going to be train our own model, so what could be the strategy? The strategy could be, first we can do the normal fine tuning, okay, to adapt the model on your specific domain. And after that, what we can do? So first we can do the normal fine tuning, and after that we can do the instructional fine tuning. Okay, and with this particular strategy, my model will become the beast. Means my model can generate an output according to our requirement. Okay, now the last step is called the alignment with the human feedback. So for that, so here you will find out data. So in which way the data will be available. So pair of response ranked by the human. Okay, means human is ranking the response, whether it's good or not, whether it's a positive, negative, something like that. Now for that we have RLHF technique, DPO technique, RLAIF technique. But guys, this technique is a very basic and useful, so we'll go with this particular technique. But when I will explain DPO in the detail, definitely I'll give you the glimpse of this technique as well. Okay, this technique RLHF and this RLAIF, reinforcement learning from the AI feedback, I'll discuss about this as well. Now what is the goal of it? To make the model polite, safe, helpful, and aligned with the human value. Now LLM has generated an answer, that's fine, but human is liking this answer or not. Okay, human is liking this particular answer or not, we don't know about it, right? So what we'll do, we'll again perform the training. Using this DPO technique. Again, it's a supervised training only, and I will show you how the data looks like. So I kept some of example over here. GPT-4, pre-trained GPT, supervised fine tuning. Okay, with the there's a instruction fine tuning, and then RLHF. Gemini also SFT, RLHF, and then multimodal alignment. Okay, DeepSeek also they have trained in the same way. Okay, all the steps they have followed. Now ChatGPT, right? For the GPT, how they have collected this human feedback data. So they have collected from the log, okay, from the ChatGPT user log, means whatever answer is being generated, whether a user is giving thumbs up or thumbs down. Okay, so that particular log they were capturing, and that was a data, right? So collected with the user consent and anonymization. Okay, so whatever user is giving the feedback, okay, based on that that particular data they have filtered, okay, and again on top of that data they have retrained the model, right? So likewise they have captured the data for the chat gpt, for building the chat gpt, okay, for training the gpt model on the human feedback. Now this particular example I kept for the gpt model itself, for the chat gpt, but in our case we'll have to collect our own data if we are going to build a chatbot like this, okay, on our own LLM, right? So I hope guys this thing is also clear. Now let's see some family wise breakdown, Llama, Gemini and all, and then basically I will go with the different data set. And first we'll start with the non-instructional fine tuning, okay, and in the next video I will show you the instructional fine tuning. So here I kept the family wise breakdown, means I kept the different family of the model like Llama, GPT, Mistral, DeepSeek and Gemini. So let's look into all these three stage of the training with respect to these model. So stage one, let's say Llama, pre-train on trillions of token. The data would be the common crawl data, books, coding and all. Then in the next stage we perform the SFT, supervised fine tuning. So we have made this Llama to chat. If we want to make it to the human, if we want to align with the human responses, right? So we did the third, we have performed the third stage, okay. Then public wise, so Meta released both base and the chat variant, right? So you can choose base or chat. The chat model basically it's aligned already, okay. Means they have performed the instruction fine tuning as well as they have aligned with the human feedback. Now if talking about the GPT, so GPT-3 which was released in 2020, it is a pre-trained model only. Then Instruct GPT they have released in 21. You can check out with this particular model. They have performed the SFT, means instructional fine tuning as well as the RLHF. Then in 2022 and 23 they have released the GPT 3.5 and 4, heavily aligned with the RLHF and safety filters, okay. And again it was an instruction fine-tuned model. Then GPT model are closed source, so you don't get base bait over here, means you cannot get this particular model because it is closed source. They are just giving the API, directly use the model. If you want to fine tune on your own data, if you want to perform the instructional fine tune, that is possible, okay. I'll discuss that. Now Mistral wise, same thing. So Mistral 7B is a base model. This particular model was released in 23. Then 8x7b model, this is a mixture of expert, again it's a base model which again released in 23 itself. Then instruction version of the model, this model was released, you can check out with the repository of the Mistral. Then some model also aligned with the RLHF and DPO, okay, you will get inside the repository itself. Open weight released means we can also use the base model as well as the instruct model directly, and we can fine tune for our own requirement, okay. DeepSeek again in a same way. So they have released the base model, pre-trained model, okay, in all the variants. Then they have released the DeepSeek code model, okay, which is trained on the code data. It was the SFT training. Maybe it was the instruction fine-tuning training. Then they have released the R1, okay, this was again aligned with the human feedback, right? Now open weights is available. It is a China's big open source push. For sure you can download this model from the Hugging Face itself. Gemini again same thing, right? So this was the family wise breakdown guys, and similar to that you will get the cloud based model, right? Opus, Sonnet and all, and yes, they have also trained in the same manner. So unsupervised pre-training, then domain specific fine tuning, non-instructional, then specific fine tuning, instruction fine tuning, and then RLHF. Okay, these are 4 stages. Let me revise all this thing over here. First is what? So first is the unsupervised pre-training, okay, unsupervised pre-training, UFT. The second is SFT, supervised fine tuning, again 2 part of it, non-instructional fine tuning data on this data, and then instructional fine tune data. Then third is reinforcement, preference alignment, preference based learning on human feedback, okay, on human feedback. Now we're talking about the GPT model, the chat GPT product you are seeing, okay, or any other product which have been released by any other company. So they have performed the unsupervised pre-training, then they have performed the supervised fine tuning, means instruction fine tuning, and then this preference based alignment. Now if you are doing for our own company, our own company, so we cannot, okay, if we are doing for our own company, so we cannot train the model from scratch. It is not possible. So what we'll do, we'll pick the base model, we will train it on our non-instructional fine-tuned data. If I want a structure output, in that case I will go ahead with the instruction fine-tuning. Okay, first this, then this, then this, and then if I want to be aligned with the human answers, then I will perform the preference based alignment, okay, through the human feedback. Okay, so here I will go ahead with the DPO technique, right? So this is the entire summary of this theory. Now we'll see the practical, guys. Now for the practical, guys, I created Google Colab notebook, and you can see the title of the notebook: non-instruction pre-trained LLM fine-tuning on a domain specific data set. Okay, so let's connect to the GPU. Now here you need to change to the runtime. If you haven't changed, then change to the GPU and then save it. You can purchase the Google Colab Pro if you want some premium GPUs like A100 L4 GPUs. Okay, you can work with it after purchasing the Google Colab Pro. I don't have Google Colab Pro right now, so that's why I'm working with the free GPU itself. So I written the title, I connected with my GPU. Now let's start with the practical. Now first of all, guys, let me show you the data set. So here is my data set. So this data set is belong to the pharma domain. Okay, this is the dummy data set. Here I just have one page because I just have to show you how to fine tune our model, how to fine tune our pre-trained model on top of the domain specific data set, which can reside in any PDF, any document. Okay, so this is the plain text only. You can see here we don't have any sort of a CSV, we don't have any sort of a column right now. Okay, we just have plain text. So we'll transform this particular data, okay, into the appropriate format, and then we'll pass it to the model. So this is our main name. Now here for performing the practical, guys, I am going to use the Hugging Face. So let me show you the library, what a library we're gonna use for training. So here, guys, we are going to use transformer library. We're gonna use the dataset library. Okay, then accelerate we are not using because this library is for the multi GPU setup, but yeah, we'll install it because some dependency onto this accelerate. Then we'll use the bits and bytes. Okay, this is for the loading the quantized model. Then PEFT library, it is for the LoRA configuration, right? So LoRA, prefix tuning, adapter, everything we can do using this PEFT library. Now you can see the further detail of this library. So who has created this library? Hugging Face only created this transformer library. Same dataset library been created by the Hugging Face. Then accelerate library also created by the Hugging Face. This bits and bytes library is created by this specific guy, Tim Determers. So this library is available under the Hugging Face. Okay, this bits and bytes, you can directly install it from the Hugging Face itself. Now PEFT library, it is also created by the Hugging Face. Okay. Now the key research paper, GitHub and all, you can search because it is an image, or else what I will do, I will give you in the description, you can take from there itself. Now after that, guys, what we have to do, we have to install all this library. So for installing this library, this is the command: pip install -u peft bits and bytes transformer and accelerate. Okay, now guys, after installing it, I required one more library. So the next library is the TRL. Okay, this TRL, the full form of this TRL is transformer reinforcement learning. So for performing the supervised fine tuning, we required this TRL library. So let me install this also. Now we required one more library. So we required this PyMu PDF because my data is residing into the PDF. Okay, so we have to load the entire data from the PDF, and for that we required this PyMu PDF library. Okay, so I hope till here everything is fine, everything is clear. Now first of all, guys, let me show you how the different data looks like. Okay, so what I'm doing, guys, I'm going to copy and paste the different data set link over here. So first, let me show you this non-instruction fine-tuning dataset. So this dataset actually it's a pre-built dataset, means already you will find out this dataset over the Hugging Face. So you can look into these dataset, and if you want to use this particular dataset just for the practice, okay, or just to train any model, you can directly take it from there. Okay, this is a pre-built dataset which you will get from the Hugging Face itself. But guys, in our case, we are going to fine tune on our own custom data. So this dataset is not available over the Hugging Face, means this is the we are assuming that this is our own enterprise data. This is our own company specific data. This is our own customized data. Okay, so we are going to be loaded from the PDF. But already over the Hugging Face, you will find out so many dataset, the non-instructional fine-tuning dataset, instruction fine-tuning dataset, and even the DPO dataset. So what I'm doing, I'm keeping some name over here. So here, see guys, these names belong to the non-instruction fine-tuning dataset. Okay. Now, likewise, I can give you the instruction fine-tuning dataset so that later on you can go through with it. So here is the link of it. Okay, directly I kept the link of the instruction fine-tuning. I kept it in my notebook. That's why I'm directly copy and pasting from there only. Then I have one more type of dataset, that is preference alignment dataset. Okay, so let me show you that particular dataset also. So here is the preference alignment dataset. So if I'm going to show you, see, let me show you the dataset how it looks like. If I'm going to show you this fine web dataset, okay, I already opened this link. See, this is the dataset. It is available under this Hugging Face FW repository. The dataset name is Fine Web. Okay. So see, inside this particular data, you will find out this text column. So entire data has been divided into the multiple rows. Okay, and it is available under this text. Means the entire plain text. Okay, it has been divided like this. So we have to prepare our own data. Okay, this customized. We have to prepare our own data, this PDF data, into the same format. So let me show you the PDF data. See, this is the PDF data. No? It is a plain text, right? So this was also the plain text, but this particular data have been prepared like this to feed to the model. Okay, so we have to prepare our data, PDF data, into the same form. Now let me show you the another data. So this is one more data, the pile PubMed abstract refined by data juicer. So guys, this is this data set actually belong to the pharma research paper. Okay, now here inside this text column you will find out the abstract of all the research paper, right, inside this particular column. Now this particular data is refined by this library, data juicer library. Here you can see this data juicer library, which is used to pre-process the data. Okay, that's why the name is like this. The name is the pile PubMed abstract refined by data juicer. Now see, inside this table you will find out this text column, and under this text column you will find out the entire data into the multiple rows. Now the other column actually it belongs to the metadata, so you can ignore this particular column. Now while we are creating the data, at that time you will get this particular column, but yeah, you can create this particular column, but again there is no use of it. The main use of this text column only. Now let me show you one more data. See, here is one more data, sky line. So inside this repository, sky line 007, under this repository you will get this open web text data. So this data set, see here you can read out the definition of this data. This is the open source replication of the web text dataset from the OpenAI. Means whatever dataset have been used by the OpenAI, it is a replication of that. Now this dataset is very huge. Okay, this dataset was used to train the GPT-2 model. Now here you can see the size of the dataset. So total size of the dataset is 55.21 GB. It's very huge dataset, guys. Now here you can see the example. So under this text column only, the data will be residing into the multiple chunks, into the multiple rows. Okay, so there could be a tabular format, or you can look into the means the data they can show you into the JSON format. Okay, but the column name would be the same text only. Okay, so we have to prepare our own data in a same format. Now let me show you the other data set. So here I can open that data set. Where is the file? So here is a file, guys. So what I'm doing, guys, I'm going to be open the other data set. Let me close it. Step by step I can open. Okay, so guys, here in the instruction fine-tuning data set, I'm going to be open this particular data. The data set name is what? Mental health counseling conversation. Now this is the instruction fine-tuning data set. Now here you will find out the context, okay, and the responses. So this is the question, right, and here is the response of it. So the data you will find out in the form of instruction and the responses. Okay, so you can think in such a way: this is the input, this is the output. Okay, this is the question, this is the answer, this is the instruction, this is the response, this is the context, this is the response, anything you can say. Now I can show you the other data. See, this is the next data, alpaca, this clean data. Now inside this data set also you will find out this output instruction. Okay, output instruction, input column is empty over here. Okay, now you can look into the other data set. See, open ORCA data. So inside this particular data also, what you will get, guys, you will get this system prompt, question, and the response, right? So in every instruction fine tuning, in every instruction data set, okay, in every instruction fine tuning data set, you will get the question as well as the response of it. Now I can show you the preference alignment data. Okay, so this particular data was created by the Anthropic, public by the Anthropic, just for the practice, or like how the DPO, how the this preference alignment data looks like. Now inside this particular data, you will find out two columns. First is a chosen, so whatever answer is chosen by the AI, and the rejected. Okay, whatever answer is rejected by the AI. Now I can show you from the different repository. See, here is from the different repository, so you can you can check this ultra feedback binarized preference clean. So inside this particular repository also you will get two columns. One is prompt and second is chosen. Okay, and then another column you will get rejected. Okay, so chosen and rejected, this will be the common column in every preference alignment tuning data set. So you can look into the other data set. See, let me show you the last one also. So here is the last one. So guys, inside this particular data also you will find out the prompt, initially region step, chosen, and then there will be one more column, rejected column. Okay, so guys, in every data set, right, which is belong to the preference alignment, you will get the chosen as well as the rejected. Now I hope you got to know how the non-instructional data, instruction data, and the preference alignment data looks like. Now this data set is already given by the Hugging Face. Okay, so this is the pre-built data set, right? But guys, we are not just doing the practice using this pre-built data set. Many YouTubers, on many YouTube video you will find out this kind of tutorial. So we are doing on our own custom data set. So in this particular video I will show you with the non-instructional data. Okay, so this non-instructional data, this text column, we are going to be create from our PDF or data itself. This is our PDF data. Okay, now in the next video I will show you the instruction fine tuning on the same data. Means we'll create instruction data set from the same domain. Okay, thus from the same kind of context to make our model more better, and then the same model will train on the this preference alignment data. Okay, in the next video I will create one preference alignment data. Okay, and on top of that particular data will train the same model. So we took the we are going to take the base model. So first we'll train on this non-instructional fine tuning data set, which is our PDF. So here you can see this is my PDF. Okay, now after that we'll train on this instruction fine tuning data set in the next video, and then in the next video we'll look into this preference alignment data. I hope now everything is clear. So let's start with the practical. So first of all guys, what we'll have to do, we'll have to load our data set. Now before loading our own data set, the custom data set, let me show you the inbuilt data set. Okay, so how the inbuilt data set look like. So first let's load the pre-built data set. Now guys, I already written the code in the notepad, so I can directly copy and paste from there because this code is prepared by me itself. So first of all we'll have to import the data set. Okay, so from the data set guys, I am going to import two things. So let me import two things over here. The first thing is a load data set, and the second is the data set itself. Just a second, let me check what is happening. Okay, so guys, here I loaded this, here I imported this data set as well as this load data set. Now what we are doing guys, so here you can see we are going to load this tiny story from this particular repository. Okay, this is the data set actually. Again, it is a non-instructional tuning data set. Okay, this one. So I can show you also. So I can just copy this particular name and I can paste it over here. Now here see, you will get the very first link, right? So just go through with this link and see here is a text column, only the text column. Okay, so this data set again have been divided into the multiple rows. Now what I'm doing, this is a pre-built data set, okay, from the Hugging Face. I just want to show you how the data set look like. So if I'm going to print this data set, so what I'm doing, I'm going to be right over here, print data set. Now see how the data set look like. So let me copy this data set, and this variable I am pasting over here. Okay, so this is my variable. Now see, so okay, first of all we'll have to load it. This loading might take time. Okay, it's loading. Fine. So see, the data is loaded. Okay, so guys, the data is loaded successfully. Now after that, what I'll do, I'll print the data set. See, here is a variable. Here is the dataset variable. Now inside this dataset, you will get the feature. Only one feature I have, and see the number of rows. So how many rows we have? We have 21,19,719 rows, means almost 2 million rows. Okay. So guys, but we are not going to use this data set. Instead of that, we'll create our own data set. So let me show you a couple of rows from here. So let's check with the first row. So here you will get the first row. See, this is the first row. Now let me show you the second row. Okay. So here is my second row, this one. Now if you want to check the last row of this data set, so simply you can write over here -1. See, here is the last row. Okay. So guys, this data set was a plain text, and now this data set was divided into the multiple chunks. Okay, multiple text chunk, and under this text column you can see the data. Okay, number of rows. Now we have to convert, okay, our PDF into the same format. If I want to train the model on top of the PDF, okay, so we'll have to convert into the same format. So how we can do it? So first of all, guys, we'll have to load the data. So for loading the data, let me write a heading. I will share this notebook. You can completely follow this notebook. Okay, I'll give the link in the description itself. So here is the basically custom data. Okay, so you can see the heading. Now what I'm doing, guys, I'm going to be import the feeds library. This is from the PyMu PDF itself, means in the backend it is using the PyMu PDF. This feeds library we use to load the PDF. Now here I've created one function. My function name is what? Extract text from the PDF. Okay, so I will give the PDF path. I will take the text. I will load the text inside this particular list. Okay, I will open the path. I will iterate on top of the pages. Okay, I will collect the data from here and I will append inside the list. Simple logic. Okay, and then I will return this particular list after completing the loading. So let me give the path. So here is my path: content format.pdf. Now once I'll run it, guys, so what I'll be getting a data. So here it is saying the data is not available because first we'll have to upload the data. If you're not going to upload the data, guys, in that case you will get a same error. So please make sure that you are going to upload the data over here, or else you can read it from the GitHub, you can read it from the drive, anywhere you can keep this data and you can read it. Now what I'm doing, guys, so here let's try to read the data now. So see, I got the PDF text. I can show you how the text looks like. So this is the text, guys, the complete text which I am able to get from the PDF itself. Now after that, what I'll do, I will divide the text into the chunks. Now this divide the text into the chunk, it is a hyperparameter. Okay, so this logic, basically what we can do, this logic we can decide how we are going to be divide our data into the chunks. Okay, and what would be the size of the chunk, right? Now I can give you a couple of examples, so I kept for all of you. Now first of all, guys, see, whenever we are going to load the data. Okay, so this is the complete step which we need to follow. As of now, my data was not too much, but if we are going to train our model from scratch, okay, or if we are going to do the non-instructional fine tuning, so you need to follow the same step. So first you need to collect the data, which we have already done. So see, this is my data. Now after collecting the data, guys, what we have to do, we have to cleaning and filtering the data. Then we have to divide the data into the chunking, okay, multiple chunks, because we cannot give this entire data at the single go, right, to train my model. Then tokenization means we have to convert our data into the specific numerical ID, okay, after the chunking. So to every token into the given chunk, one ID, one numerical ID will be assigned, and then we are going to perform the training, which is the next token prediction, right? So this entire step we have to follow. Now guys, here I kept one more thing, one more table. So this table could be very much important. So just try to read this particular table carefully. So here I given the model name, max to context window, approx word, how many words could be there, and the comment, right? So GPT-1 model, so it was able to handle 512 token, and there was approx 350 words. Now GPT-2 1000 token, okay, around 750 words. GPT-3 2000 token, 1.5k words around. GPT 3.5 409k token, around 3k word. And if we're talking about GPT-4 40, so it is able to handle up to 1,28,000 token, around 1 lakh words. Okay, Now over here guys, you can see, so whenever we are going to chunk the data, okay, so we have to keep something in our mind, right? So our model, right, how much basically token can handle, and whenever we are going to be divide the data into the chunks, okay, so we can follow some regex pattern also, means we can divide our data into the paragraph, we can divide our data into the segment, okay, or a semantic chunk and all, and then basically we can or else basically we can go ahead with the token length also. So let's say if we are going to be train GPT-4 kind of model, so let's say we are going to be load the data, this PDF data, okay, so we can give the bigger chunk to the GPT-4 model to retrain it to the fine tuning it, okay, and similar at the time of the unsupervised tuning as well, okay, means the first step, the initial stage, okay. Now here guys, you can see, so this chunking we can do based on what, based on this particular pattern. See here I written based on the paragraph, semantic chunking, right? We can write some regex rule and all, and then we can, or else we can go ahead with the token length, means how many tokens we can bear in the single chunk. According to that also we can define the chunk, or else we can take the both strategy, okay. So I written a function over here. Now see the function, so it's split paragraph. So first we'll take the pages, okay, this data. Now we are going to be split based on the line, okay, based on the new long line, means the double line. Here you can see in the PDF itself. So if you will look into the PDF, so where it went here, so here you can see between this line and this line we have major gap, right? So we are going to be divide our data into this based on this major line, okay. So this is the regex pattern. You can write any regex pattern. You can read out the chat GPT model research paper, any other research paper, right? How they have done the unsupervised pre-training, how they have divided the data into the chunks, the entire text and all, right? So it will also help you, okay, but this is also a generic practice. Then what I'm doing, I'm iterating on top of the chunk, and if I'm saying over here, if there is a 30 character, more than 30 character, then only I'm going to be append the chunk into this particular list, okay. So whatever like whatever pages we have is on, we are iterating on top of the data, okay, and on the entire list, then we are chunking based on this strategy. If inside this chunk we have more than 30 character, more than 30 character means what, 10 to 12 token, okay, or 8 to 9 token. So more than 30 character only, then only we are going to append inside this particular paragraph, okay. So if I will run it guys, now here you will see we are going to be split our data. So here inside this particular variable I'll get my data, split data. Now see, so see what I have the first chunk, then second chunk, okay, then third chunk, then here you can see the fourth chunk. But guys, the data should not be like this. The data should be available into this particular form, okay. We should have this okay, we should have this text column, and under this text column the chunk should be present. So what I'll do now, I will map my data, okay, to the text column, okay. Now here what I'm doing, I'm iterating on top of the chunk, and then I'm assigning it to this text column. So now how my data look like. So if I'll show you the data, so here see my data guys, we have this text, okay. Now with every text one chunk is associated, chunk text, okay. Now what I'll do, I will convert this particular data into the Hugging Face compatible data. So for that I have a dataset library, okay, which I already imported. Now from here I will call this from list, okay, from underscore list. Now from this list itself, so here you can see this is a list only now, right? So I will pass this data to the list, okay. And now what I'll do, I'll keep it inside the variable. Let's say my variable name is dataset, okay. Now see, my Hugging Face compatible data is ready. So if I will show you this dataset, so how may the dataset look like? See, feature text, okay. Under this text we have a multiple chunks, okay, and here number of rows is 4. So if you will look into the pre-built data guys, this was my pre-built data. If you will look into my pre-built data, so this was a pre-built data which I loaded from the Hugging Face. In a same way we are able to convert our data. See, here is my data. So now you can check the first row, second row, whatever row you can check. So let's say if I'm going to be check the first row, okay, I will simply put the 0. So here you will be able to get the first row. Likewise you can get the second row, okay. So in total we have 4th row. So guys, in whatever way I was having my pre-built data, the data was already available over the Hugging Face. Now I'm able to convert my data set into the same format, okay, my custom data set. So this all the technique, all the pre-processing step you will have to follow with respect to your plain text. Now coming to the next part. So the next thing is basically we have to select the model. So first of all, let me create the multiple cells, okay. Now here we'll have to select the model. So let me make a heading. So the heading is let's select the model. So guys, model wise, what I'm doing, I'm going to be select a very tiny model because I cannot bear the large model inside with this particular GPU, with this particular memory. We require more VRAM and all. So if you have Google Colab Pro access, or you have more VRAM, then you can try out with this particular model. I'm using this model tiny from the Tiny Llama repository. So Tiny Llama 1.1b intermediate step 1431K 3T. Okay. Now, what does it mean? What is the meaning of this line? So I written a meaning of this line over here. See, so the checkpoint is from the Tiny Llama model, okay, which trained up to 1.54 million step over 3 trillion tokens capture midway before the final conversion. So guys, this particular model is a Tiny Llama model. This model trained till this particular step, okay, around a 14 lakh step, okay, on top of this much of token. So I'm using this model to train. I'm using this as a base model. This is my base model, guys. Okay, this model is not being trained on any instruction data, or not on any domain specific data. This is my base model, simple pre-trained model. Okay, so I'm going to use this particular model to perform the domain specific fine tuning on top of my PDF data, right? I already prepare a data. Now what I'll do, guys, I will basically perform the fine tuning. So first of all, guys, what I'll do, I will load this specific library like auto tokenizer, auto causal LM, trainer, training argument, and data collector for language modeling. I think this will not be required. Training argument will be required. So let me run it, and I'm going to load the library. Now here, what I'll do, guys, I will load the tokenizer. Okay, I will tokenize my data because I already performed the chunking. Now I will perform the tokenization using this particular tokenizer. Okay, so I'm loading a tokenizer. Now after that, guys, I have to execute one more line of code. So if padding is none, then in that case I'm going to be assign this end of the token to the padding, right? Now why it is required, let me give you the reason of that as well. So here I kept one image, with that you can easily understand. So guys, what is a pad token? So pad token we use to make all sequence in a batch to the same length. So let's say in input word we have 2 token, hello world, right? In input 2 we have 3 token, good morning everyone. Technically there is a 3 token, hello world, this full stop, then good morning everyone, full stop. Now here you can see the size of the token, size of the input 1 and input 2 is different. So if I want to make it same, so here what I'll do, I will do the padding. Okay, now how I am going to do the padding? So at the end, okay, at the end of this particular see here the length of this particular input is 4. Okay, 1 2 3 4. Now what I'll do, so here at the end of the sentence hello world, okay, after this particular word I will add one more token, okay, that's going to be EOS, end of the token, okay, this EOS. So if I'm going to be append the EOS token, now how my sentence will look like, hello world EOS. Okay, so the length of this input 1 and input 2 is going to be same. So that's a simple use of this line. So let me run it, and here we are able to append this end of the token. Okay, now after that what I'll do, guys, so after that, guys, we are going to be pre-process the data. Now the pre-process step is pretty simple. So here we are passing example, means every text chunk. Now after taking every text chunk, see we are truncating, okay, we are padding, and we are like defining the max length. So what is the meaning of this particular parameter? I'll tell you. Now here we have one very important line. So to token, okay, to the label actually we are going to be assigned this input ID, okay, and then we are going to return the token. So let me execute it, and let me explain the meaning of this each and every line because it is very much important. So here what I'm doing, guys, I'm going to be I'm going to be like add some example and all, and with this particular example we'll be able to understand. Now see, so whenever we are passing the text, so let's assume this is my text, okay, metformin improves insulin sensitivity in the liver. So what will happen? So this tokenizer token, okay, it is going to be take this particular text. Now truncation true, what it will do, so if the text is longer than 512 tokens, it is going to be cut off that. Padding true means if the text is shorter than 512 token, it's going to be pad. Okay, and the fixed length of this particular sentence of this like whenever we are doing the tokenization, it will be 512. Okay, if it's going to be less and more to this 512, then we are going to be truncate, or we are going to be perform the padding. So after processing it, I will be getting this particular input. So input I will be getting this particular output, where I will be having 2 column input IDs, okay, which is going to be assigned to every token, and then attention mask. Attention mask is saying which token is important for me to the attention layer. Then label, guys, so token labels, token input ID dot copy. Now why we are doing it? So this is a key step for the causal unsupervised language modeling. Means what is our aim? The model should try to predict the next token in the same sequence. Okay, I shown you how the data is being prepared for this non-instructional fine tuning. Okay, for this plain text, for this particular plain text. Okay, so we took this plain text, we convert into the text. Okay, multiple rows, we did the chunking because of the model, right? Because we cannot put the entire data in a single go to any model. Okay, and then we have to predict the next word. Okay, in the non-instructional fine tuning, we are doing this self-supervised fine tuning, self-supervised tuning itself, right? So what we have to do, we have to predict the next token, and for that what we have to do, we have to prepare a data in such a way. So here you can see the sentence. What is my sentence? Metformin improve insulin sensitivity in the liver. Now see over here, this is my input. Metformin improve insulin. Now what is the target level? Improve insulin sensitivity. So okay, so metformin improve insulin. So here what is the next word of it? So metformin improve insulin sensitivity. Okay, so the sensitivity will be picked as the next word. So this particular line, with this particular line, we are going to be prepare this kind of data. Okay, now whenever we are passing, whenever we are getting final result, so we'll be getting the input ID, attention mask, as well as the labels, right? So let me execute it and let me show you how the data looks like. So for executing, we'll have to map the data. So here what I'm doing, guys, I'm going to be map the data. So I have a data set, I'm calling .map, tokenization function is there. Batch 2 means we can pass the data into the batch if we have so many data. Okay, so many rows. And here remove column text means in the final output, we just want this three thing: input ID, attention mask, and label. We don't want this text. Okay, so I'm going to remove it. Now here I will be getting my tokenized data. If you want to check it, you can simply check it. See, here is what? Here is my tokenized data. Input IDs, attention mask, and label. Now here is the number of row. Number of row is 4. Now what I'll do, guys, I will load my model. So here you can see I'm going to be load my model. So model loading might take some time because the model size is around 4 GB. Okay, so in your it depends on your internet speed. In my case, it might take like 4 to 5 minutes. So let it load, guys. So guys, my model is loaded. It took around 4 to 5 minutes. So as I told you, it depends on your internet speed also. Now after that, what I'll do, guys, I will define my training argument. Okay, so here inside the training argument, so guys, see, we have so many training argument inside this class. If you will see the list, you will get the hundreds of argument. So how you can get the detail of it? So for that, you can simply call this help training argument. Okay, so you already loaded this class from the transformer. You already imported this class from the transformer. Now simply pass it to the help method. Okay, now once you will run it, see here you will get the detail of each and every parameter, whatever is there. Now I mentioned the required parameter only, so I kept the meaning of this particular parameter. Let me mention it over here. So output directory means where we are going to save the model. Overwrite output directory means we are going to overwrite the previous model. If we are saving the new model, it will overwrite to the previous model. Number of training epochs, how many epochs we are running for the training the model. Per device train base size means in one single go how many batch size we are passing. Save step, at which step we are saving the checkpoint. Save total limit. Okay, so keep how means how many checkpoints you want to be keep on your disk. Let's say you have five checkpoints, so you will keep only 4 and 5 checkpoint if you are writing 2. Okay, the latest 2 checkpoint you will keep on your disk. Then logging step, at which step you are going to be log. Okay, learning rate means it belong to the optimizer. So if we have very huge learning rate, my basically graph will go here and there. If we have like a small learning rate, then my graph will go smoother. So guys, if you know the basics of the deep learning, then I think you can understand the meaning of this learning rate. And now FP16 for the precision, right? In which precision basically we are going to be load the model. A report tool means we are not going to be log our data anywhere. Okay, on any basically a tensor board or any bit and bias like dashboard, right, or anywhere. So we are just like keeping none. If you want to keep, like, we can remove this none, and we can keep our metrics as log and all on some different platform. Okay, by default you will get the weight and bias W and B platform, right? So this is the meaning of this parameter. I think you got to know. Let me run it. So my models will be available inside this particular directory. Now after that guys, what I'll do, so you can check with this help method. Now I'm going to be define my trainer. So after defining a trainer, okay, so see the trainer might take some time. So trainer is taking three things. One is model, second is data, okay, this tokenized data, and the third is a training argument. That's it guys. Now after training, after defining a trainer, I will just call the train method on top of it. So trainer is a class. We are going to initialize this particular class, and then we are calling this train method. So once we'll call this train method, now guys see what we'll get. Can anyone guess what I will get? So you can pause the video and you can give me the answer in the chat if you're watching till here. So if I'm going to be run it guys, see here I will be getting out of memory error. Now why I'm getting this out of memory error? Because guys, you haven't focused, because we are training the entire model. We are retraining the entire model over here. If you will check, see we are loading the model. We are not going to be select any basically last row, okay, or the initial row. We are not going to do any LoRA and QLoRA. We are simply retraining the weight of the entire model, and my machine is not capable to do that thing right now, and because of that I am getting this out of memory error. So what is the solution of it? So the solution of it is LoRA, okay, parameter efficient fine tuning. Now before the LoRA guys, let me show you the other method also. So here I written some sort of a description. So let me keep the description over here. Okay, so what is the description guys? So here we are not specifying anything, means this is the full fine tuning. Now we have two methods for the partial fine tuning. The first, freeze some layer and fine tune unfreeze layer, which is the old CNN method or BERT style method, right? The second is LoRA, append some external weight to the already trained pre-trained weight. So guys, I will show you this both method. Okay, I will more focus on the LoRA. I'm not going to explain you this freeze some layer and all. I will give you the code. I'll keep it over here, but I'm not going to explain because I already explained in my previous video. So if you will go and check, right? So let me show you in which all video I have shown you. If you will go and check with the playlist. So okay, this is running. So if you will go and check with my playlist, so just check out with this third video and the 9th video. Okay, in this both video I discuss about this particular technique, and even I shown you the practical also. Now guys, come back to this like solution. Now here what I'm doing, I'm going to be write a code. Okay, first I'm giving the code for this particular method for freezing the layer. You can try out from your end, okay, or else you can watch out those particular video, but this is not an appropriate method. There is some pros and cons. Maybe in the later video we'll discuss, because otherwise this video will be very longer. Now here, what is the code guys? So let's look into the code, what we are doing over here. So first we are loading a model, okay, then we are freezing some layer, then we are unfreezing the last 4 layer, okay, and then we are loading the data set, then we are defining the training argument, and then we are training the model. Simple guys, okay, that's it, nothing else. So you can look into this particular method and you can run it, but this is not an efficient one with respect to the larger LLM. We'll discuss theoretically later on why it is not. I'll show you the mathematics of the LoRA, DPO, everything guys, don't worry, right, in the upcoming session. Now what I'm doing guys, so here we are going to perform the LoRA based technique. So how to do the LoRA based technique? Let's come to that. Now before running the LoRA based technique, I will run the this garbage collector. Okay, so whatever cache memory and all will be there, unnecessary memory, it's going to be removed that. Now again what I'm doing guys, I'm going to be update the library, because before running the LoRA configuration, we'll have to update the libraries, okay. Because initially we haven't installed this PEFT library, right? Bits and bytes, we also required the upgraded version, transformer and the accelerator else also. So let me run it, let me execute it. Now after that what I'll do guys, I will import this particular statement. But before that guys, what you can do, you can simply restart the session, okay? Because restart the session basically will load the latest version, okay, whatever version we require. Now after that what I'll do, I will import these packages, all the packages, auto tokenizer, causer LLM, training argument, trainer, then LoRA config, get PEFT model, task type from the PEFT, and then from the dataset we are going to load the load dataset, okay. Now after that guys, what I'll do, I'll take a same model which I was taking initially. Now here I will load the or tokenizer in a same way, okay. Then I'm going to be assigned this us token at the end of the as a paired token. Okay, so let me execute this. Now here it's the same thing. We are going to be map the data set. Okay, now which data set guys we are using? We are going to use the same data set. So here let's see the data is available or not. If not, okay, the data is available. Now what I'll do, I'll load it again because I restarted the session, so I will lose my data. Okay, I will lose the variable basically. So where is my data? Now first of all I will import this import statement. Now fits extract data. Okay, this is fine. Now pdf, this is perfect. Regular expression, this is also correct. Paragraph is there. Data, okay, data. Now data set is ready. Okay, so guys, here what I'll get, I will get my data set. So let it run, let it execute, and what I'll do after that, I will again tokenize. So guys, you need to rerun this step, restart the session, because you might get some issue with the LoRa configuration and all. That's why restart the session. So let me check. Okay, now it is done. So here I got my data set. So where is the data? Okay, so tokenizer is running. Let it execute. Okay, so here guys, it is connecting. Okay. So let it connect, or else what I can do, I can disconnect and delete the runtime. Again I can connect. Okay, okay, fine. Now it is done. So this is fine. It's loading. This is fine. Guys, it might take time. First time now it takes time. Okay, LoRa config get PEFT model. This is a like huge library. Okay, so the library is loaded. Now what I'll do, I'll load the model, then tokenizer. Now here I'm going to append the EOS token. Now this is my tokenizer function. So let it run. Okay, reconnect. Why it is disconnecting every time? Connected. Tokenizer is there. Okay, this is required. Don't know why it is reconnecting. Okay, so guys, I followed the same step and I got my tokenized data. So inside this tokenized data, as you know, we will be getting the input, attention, mask, and label. You can include this text column or you can exclude. It's up to you, right? So you can pass along with the text column, as well as you can exclude it also. You know how to do that. So I got the tokenized. Now after that, what I'll do, so here after getting a tokenized, guys, I will load the model. Okay, now this time guys, you can see we are going to load the model in the 8-bit format. Okay, so here I'm giving the model, then loading a model in 8-bit, and then device map is auto. Now it is saying bits and bytes require the latest version. So yes, we'll have to install it. That's what I was saying. Just a second guys, let me execute it. Pip install -u. Okay, so this is done. If it is giving you this particular warning, then please if it is giving you this particular error, then please install the latest version. Now this is done. So yes, this is fine. Now what it is saying, okay, fine guys, let me restart the session. So restarting a session, this issue you will get in a collab, okay, while you are working with this library. Now let me execute it. Okay, auto causal LLM is not defined, so here is fine. Okay, so guys, my model is ready and my data is also ready. Everything is done. Now here, see guys, we have loaded the quantized model. Let me write over here, loaded the quantized model, right? Now what I'll do, I'll define my LoRa configuration. So guys, we'll understand this configuration in a very detail in the upcoming session. So what is the meaning of the task type? So task type is a causal LM, means we are doing the next word prediction. Rn means rank, okay, rank of the matrix. Rolla alpha, so this is again hyperparameter. Target module Q and V, so this is related to the attention layer, okay, QKV. So Q query and V means value. So we are targeting to this particular module. Now LoRa dropout 0.05, bias is none. So we'll understand all this parameter in a very detail. So here you can see the complete list of it. It's a very huge number of parameter, but until we are not getting the mathematics of it, until we are not understanding the mathematics of it, will not be able to get the complete one. So definitely I'll show you in the upcoming session. So here I define the LoRa configuration. Now what I'll do, I'll load the parameter efficient model. Okay, get PEFT model. I'll give the model. I'll give the LoRa configuration. So this model is going to be my quantize LoRa model. Okay, quantize underscore LoRa underscore model. So yes, model is getting loaded. Let me define the LoRa configuration and see the model is getting loaded. So it's saying model. Okay, let me check what I have inside this model. Okay, so this should not be the case. Just a second, let me load it again. Actually we should get the model. I think I run that model string again, that's why it's coming like this. Okay, we should have the actual model over here. So yeah, this is the case. Just a second, because I already loaded the model now, so it will not take much time. Okay, done. Now see, this is my model, right? So here if I'm going to load it, so I'll be getting the QLoRA model. Now my training argument would be the same one. Then I have the trainer, right? So let me define the trainer. So here what I'll do, I'll give my QLoRA model, okay, then argument, then tokenize is the data set. Let me check with this particular variable. Tokenize is correct. Now once I'll run it, so my trainer will be ready. Now what I'll do guys, I will train my model. So tokenize is not defined. Tokenize. Okay, this is my tokenize. So if I'm going to execute it, my tokenize is ready. Now what I'll do guys, I will run it and my trainer is ready. Now this time I will not get any error, because what we are doing, we are going to do the LoRa based training. So if I'll do this trainer.train, my model will be trained guys. Okay, so see, I have a very less data and we are doing LoRa training, so that's why it's not taking much time, and we are just doing for the 2 epoch. So see, the training loss is here, and you can see the other metadata. So see, the training loss is 9.66. You can run it for the more data and for the multiple epochs, but that is not a case right now. Means we are not running, we are not learning that how to reduce, how to improve the accuracy and all. That will be the different thing. So for that also I will create one session, but as of now we have to learn how to train the model at least, right? So my model is trained. Now after that I can get it, I can get my model over here. See, tiny llama LoRa, and under this particular folder my model is available inside this checkpoint, right? So what I'll do, I'll copy the path, and this particular path I'll keep it inside the double quote, and this is going to be my model path. Now what I'll do guys, tell me, after training the model I'll do the prediction, right? So let me do the prediction with this particular model. Now first of all guys, what I'll do, I will load the model. Now I'm going to load the model. So here is my trained model. Okay, trained underscore model, trained on the domain specific data. So let me execute it and see, my trained model is loaded. Now what I'll do, I'll give any sort of a prompt to this model. Let's say my prompt is clinical trial demonstrate that combine atrovestine with as a TIMBY, right? Something like that, right? I took it from this particular data. I don't have the domain specific knowledge, but I kept this prompt from this data itself. See here, from this data. Okay, you can check out with the different other data. Now what I'll do, I will perform the tokenization of this data. I already have a tokenizer, so here I will perform the tokenization. Now what I'll do, I'll get an output. So here model.generate. Now which model? Trained model. Okay, So train model dot generate input max token this much, temperature, top speed, do sample, repetition, penalty. So these are all the parameter which we can pass, but you just need to focus on this input. Now once I'll run it guys, I will be getting my output. Now here I'm going to print my output. So let me decode my output, and tokenizer dot decode, and I'm giving the output over here. Skip special token, I'm going to be skip that. Now let's see the output. So guys, see, this is the output. Critical tries demonstrate that combining epsilon with that, right? So guys, here what we have done, we have performed the non-instructional pre-train LLM fine tuning. Means we took the pre-trained LLM and on top of our domain specific data, we have performed the fine tuning, and we are able to get the very amazing result. But guys, here let's say if we are asking any sort of a question and my model is not able to generate that particular answer in that tone, specific structure, for that what we will do, we will do the structure fine tuning, instruction fine tuning, right? So now on top of the same model, in the next session I will show you the instruction fine tuning, so that we can ask the question, right? More structured question, it can generate the answer according to that. Now guys, let me discuss what all point we are going to discuss in this particular video. So the first is what is the instruction fine tuning, then how the data looks like in the instruction fine tuning. Then we'll see why it is called the supervised fine tuning, as I discussed in the previous class that this is instruction fine tuning comes under the supervised fine tuning only. Then I will come to the practical, right? So this each and every point I will discuss throughout this video, and yes, at the end you will learn how you can fine tune your LLM model on the instruction based data. Now guys, without wasting a time, let's start with the video. Let's understand the theory first, and then I will come to the practical, guys. So guys, before starting with the instruction fine tuning, let's take a recap of some previous points. So the first thing is, what is the meaning of the fine tuning and why we do it? So here is a definition. Fine tuning means retraining an already trained model on your own specific data set. So guys, here if I'm talking about the model, right? So the model is nothing, it's a LLM model. Now this LLM model, it is based on the transformer architecture, as you know. So let me write over here transformer. So this transformer is nothing, it is a research of the Google which was published in 2018 itself. Okay, it was a sequence to sequence architecture where we were having two main things. One was the encoder and the second was the decoder. So the GPT model, right? The GPT model actually, it was built on top of the decoder part of the transformer. So if you want to understand the LLM, then before coming to any LLM architecture, understand about the transformer, okay, and then jump to the LLM. Now here I'm saying LLM, right? So we are going to be retrain already trained LLM, and if I'm going to be talking about the training, right? So what are we gonna train here? So we're gonna train weights and biases, okay? So weights and biases. Now this weights and biases, where you will get this weights and biases inside this transformer architecture. So we have attention, right? We have attention layer inside the transformer plus neural network. Okay, so this transformer, one single block of the transformer, it is a combination of the attention layer as well as the neural network, right? So there we will get the weight and biases, and yes, if we are going to be train our model, means we are going to adjust the value of this weights and biases based on that loss function and the optimizer. And if we are going to be again retrain it, in that case also we are going to be adjust the value of the weight and biases according to your data. Okay, and that's a whole sort of a meaning of the training or retraining, right? So I think you understood about it, and if you don't know about this basics and all, then you can follow my previous video. There I already discussed about this thing in a very detail along with the practical, right? Now if we're talking about the LLM training process, so in the LLM training process, the three stage plays a very important role. The first step is called the unsupervised pre-training, or it is also called the self-supervised training, which we are doing on the common crawl data set. So generally we consider the internet data over here, the entire internet data. Okay, then the second thing is called the supervised fine tuning. Now inside the supervised fine tuning, I discuss two things. The first first behalf on the parameter, okay, and the second based on the data, right? I will again give you that recap. The third was the preference based alignment or preference based training. Now here whatever output we are going to be generate, right, from the AI, from the model. Okay, so based on that particular output, based on the feedback of the user, again we are going to retrain our model, right? So that comes under this preference based alignment. So here we have very popular algorithm that is called a PPO, right? It is a reinforcement learning based technique. Now apart from the PPO, we have one more state of art technique that is called DPO, okay, direct preference optimization. So we'll discuss that in our next video, okay, and even I will show you the mathematics and all in my upcoming videos. So guys, here my main focus onto this supervised fine tuning. Now let's take a recap of it. So as I told you, if we're talking about the supervised fine tuning, so we can divide into two sections, right? So one basically it is based on the parameter. Already I discussed this thing in my previous video. I'm just giving the recap of it. And the second behalf on the data, right? Now if we're talking about the parameter wise, so parameter wise, the first one is called the full fine tuning, okay, full fine tuning, and the second is called partial fine tuning. Okay, partial fine tuning. Full fine tuning means we are going to retrain all the parameters, okay, inside the model. Whatever parameters we have, we are going to train all the parameters. So generally we don't follow this particular technique. So we always go with the partial fine tuning, means we take subset of the parameter over here, okay, subset of the parameter. Now we're talking about the partial fine tuning. So we have two techniques over here. The first technique is called the old technique, okay, old technique. Now here's in the old technique, what we are doing, we are going to be freeze, okay, we are going to be freeze some layer, okay, and we are going to be train some layer, right, some layers, okay. But guys, in terms of LLM, we don't follow this particular technique, right? Instead of that, we have second technique that is called PEFT based technique, parameter efficient fine tuning technique. And in that, LoRA is a very famous technique, right? So LoRA is very famous technique. Now apart from the LoRA, I discuss couple of more variants of the LoRA, couple of more techniques. So if you want to understand that, you can watch out my previous video. There I discuss in a very detail. Okay. So here you understood, we are going to perform the partial fine tuning, and in that we're going to discuss about the PEFT, and LoRA is one of the way to follow the PEFT, okay, to perform the parameter efficient fine tuning. Now the second is based on the data. So if we're talking about the data, guys, so data we could have, okay, let me take a different color over here. So data basically is available, right, in a non-instructional format, right, in a non-instruction format, or this is also called the plain text. Now this plain text, it would be available in any sort of a document, okay, in any sort of a document. Now this document could be the PDF document, this document could be the PPT document, this document could be the docx, right, this document could be anything, right, wherever basically we'll find out the plain text, that comes under this non-instructional category. The second data, the second type of data is called the instruction data, okay, instruction data. In instruction data, actually how it looks like, I will show you that. So instruction data, actually there we will be having input column as well as the output column, okay, as well as the output column. So guys, this supervised fine tuning, this specific term actually, it is being used in terms of this context, in terms of this instruction data, okay, where actually we have an input and we have an output. If you will think about the machine learning, right? So in the machine learning, guys, we have supervised machine learning, and in the supervised machine learning, what kind of data we have? The data where we have an output column, okay. So in whatever data we have an output column, and we are feeding that data to the algorithm, any algorithm, it's a decision tree, XGBoost or SVM, right? And behalf on that labels the Y column if my model is learning. So that is what? That is a supervised learning. In a same way, guys, this SFT actually is, okay, so because of this instruction fine tuning only, it is called the SFT, means we have an input column and the output column. So then what is this non-instructional data? Okay, means it does not comes under the supervised fine tuning. I would say no, not directly, because this instruction fine tuning technique, right, it is only called because of that only we call it the supervised fine tuning. Why? Because we have a labeled over here, okay, the output column, right? Now guys, over here, what we are going to be do, see, now one more thing, let me tell you over here. If we are talking about the LLMs, right, so whatever technique we are discussing, right, let's say in whatever stage we are, so let's say we are at first stage, at this particular stage, unsupervised speed training or self-supervised learning, there also we are going to predict the next token, okay. Now if we are at this particular stage, SFT, supervised fine tuning, at this stage also we are going to predict the next token. We'll format our data in such a way that model will predict the next token only, right? And in the preference based alignment or in this particular like technique, again we are going to predict the next token. So in whatever way we have a data, right, it doesn't matter, let's say we have a data, the entire internet data without label, in that case also we'll arrange a data in such a way that's going to predict the next token. If we have a data in the instruction in the output format, in that case also we are going to predict the next token. We'll format our data in such a way, we'll predict the next token. If we have a preference based alignment means we have generated output as well as the feedback regarding that, in that case also we'll format our data in such a way that model is going to predict the next token, okay. So as it is a language modeling, and model will always predict the next token in whatever way we have a data, okay, at whatever stage we are going to be perform the training, right? So I hope guys this thing is clear. This is the fundamental which I already discussed. Now let me talk couple of more points. So here I have written why it is called the supervised fine tuning. So in pre-training, that is a first stage, right? There we are doing a training on top of the entire internet data, where actually that particular stage is also called the self-supervised learning, means the label will be the next token itself inside the sentence. So there actually what we are doing, so in the pre-training data, model predict the next token from the natural text itself, right? But if we're talking about the instruction fine tuning, there also model is going to predict the next text, but we have curated data in such a way that we will be having the target column, okay. So in instruction fine tuning, model predicts the next token only, but from the human curated target answer. I will show you the example, and because of that it is called the supervised fine tuning, means this instruction fine tuning is only called the supervised fine tuning. So guys, over here I can give you the quick recap. If we're talking about the LLM training process, so we have 3 stages: unsupervised, speed training, or self-supervised. There's the first stage where we are going to be create our raw model. Second is called the supervised fine tuning, where we have already seen about the partial fine tuning, that is called PEFT, and that is a LoRA, okay. This is based on the parameter, right? How many parameter we are going to be select while we are going to be train the model. Now data wise, how we are going to prepare the data while training a model. So we have 2 ways. First is the non-instruction, where we just have plain text, right? And second is the instruction based data. Now because of this instruction based data, we end up with this specific name that is called the supervised fine tuning, okay. But guys, if we just have plain text, then ideally we should not say it's a supervised fine tuning, means here we will say we are just going to be fine tune our model, okay, on top of our domain specific data, okay. Now I hope everything is clear. So let's do one thing. Let's take some example, and then after that we'll start with the practical, guys. Now guys, let's revise the differences between the non-instruction and the instruction fine-tuning, and after that I will let you know why this instruction fine-tuning is required, and then we'll move to the practical. So non-instruction fine-tuning, first let's discuss about this one. Non-instruction fine-tuning, so fine-tuning on a plain text means teaching the model your domain language. Now what's the purpose of it? So the purpose is to help a model to learn the language, tone and the terminology is specific to your domain. Okay, so let's say if you have this type of data, the plain text which is available in any sort of a document. So on top of this data, we are going to be retrain, or we are going to be fine tune our LLM model. Now in which format we are passing our data to the model. So the data you will get at the end, you will get in this particular format, means we are going to put the next token. Okay, so the next token will be in my output column. So let's say this is my sentence. Okay, so this is the next token regarding it. Now this is my sentence. Now here is the next token. Now this is my complete sentence, and this is the token, right? We already understood in a previous video. So let me give you one more concept over here. Let's say there is one company, let's say there is Meta. Okay, Meta has trained one model. The model name is Llama 4.2, something like that. Now you want to be use this particular model inside your organization. Okay, so you belong to, let's say, pharma. Okay, pharma. Now in your company, in your organization, you want to be use this particular model. So what you will do? So you will directly take a model and start using it? No, this is not a right thing, because this model does not know the pharma specific term. Right, this model does not know about the pharma specific term, so it will hallucinate. So what you will do here, you will fine tune, you will go with the fine tune. Now here for the fine tuning, directly you will fine tune on the instruction data set, means directly you will fine tune on the input and output data set. You can do it. You can teach your model. Okay, you can teach your model, if this is the input, then regarding that what will be the output. This is only called the instruction tuning. But guys, this is not a good practice. Okay, directly to teach your model on a input and output, it's not a good practice, right? So in between, what you can do, you can take your data, company specific data, okay, from wherever you have collected that. So you will be have a big corpus, okay, for your company data. Then first perform the non-instructional fine tuning. Now with this particular tuning, your model will understand your data, right? It will understand the specific vocabulary, it will understand the terminology, it will understand the technicality of your data, means overall it will deep dive into your data, right? And after performing this particular step, the non-instructional fine tuning, then come to this stage where you are teaching to your model the more structured output based on the given input. I hope this thing is making sense. So that's why guys, this step, okay, most of the like YouTube video will not teach you this thing. This particular stage is very much important, and I already covered in my previous video. You can go and check. Now coming to the instruction fine tuning. So in the instruction fine tuning, you will get a data, right, in the form of instruction, in the form of input. Okay, so let's take an example of it. So first of all, let's discuss the purpose. So what is the purpose of it? To train the model to understand instruction and generate well structure and the relevant answer. Okay, so to generate a structure and the relevant answer based on the given instruction. So you will find out a data in this particular way, in this particular format, where you will be having the instruction, you will be having the input regarding the corresponding input and the output. So instruction, summarize the following paragraph. Now this is the input regarding it. Okay, and we are going to be summarize. So this is my summarization. Here is my summarize output. So after giving this particular input, we should get this kind of output. Okay, so this is my instruction. Now without input also you will find out some sort of a rows. So let's say you have an instruction list application of AI in pharmaceutical research, means here you are giving input and then this is the corresponding output. Okay, now here one more example. So explain a mechanism of the metformin. Now we don't have any sort of input. Now here is my output. Okay, so in this way also you will get a data. So this data set format was followed in the alpaca, right? So if you will check with this alpaca, right, so this is one of the data set which was prepared by the researcher. I will show you the research paper and the Hugging Face dataset and all everything. I think I showed in my previous video, you can check over there, right? So in this format only the dataset have been prepared. But apart from this one, you will find out dataset in some different format also. So this is the one format: instruction, input and response. As I told you, this is the alpaca, right? Apart from that, you will get the instruction. This input could be the context and this response could be the answer. In this format also, you can also prepare the data. You can directly prepare the question answer data as a user and the assistant. Okay, in user column you can give your questions, and in assistant you can write your answer. You can give the you can prepare the data in this format also: system, user and assistant. Okay, this is also a way to prepare data for the instruction fine tuning. Otherwise, context and response. See, here I kept one example for the context and the response, guys. So I hope this thing is clear in which format actually you will get a data for the instruction fine tuning. Now here is one more point I written, I missed this part, so you can read it out. If instruction uses as extra text, means if you have a instruction and the input, right? So in that case mostly you will find out we are saying to the model, do the summarization, translation, rewrite. You can go ahead with this particular example. So here we are giving an instruction to our model with respect to this input, and then we are generating this output. Now here you can see the second line. If instruction is a self-contained, okay, if instruction is having the self-contained context or dialogue style or conversational data, then you can keep input empty, means this thing, right? I just written it as an extra note, and I think you are able to get it. What I'm trying to say here means, if we have an instruction, then we are giving an instruction with respect to this corresponding input. If we don't have any sort of input, means in the instruction only we are keeping some context, okay, some question, and regarding that here is the output. As simple as that. So I hope guys you understood this entire thing. Now the biggest question, how you are going to be generate this instruction data, because in every company, let's say if I'm taking example of any XYZ company, any ABC company, or any YXZ company, everywhere you will not find out this kind of data. Okay, sorry, not this kind of data, means instruction data. So what is a way of preparing the data, the instruction data? Okay, the first way, see here, now the question is how to prepare the data for the instruction fine tuning. Means in your company, let's say the data is available in the PDF, right? So this is the biggest hurdle. You have trained, you have done the non-instructional fine tuning, but how you will teach your model to generate the structure answer, right? So for this one, for generating a structure answer, you will have to prepare that kind of data, input and output. How you will do that, right? So here is a way. First, you can do it manually. You can write your own like question, means you can only create your question and answer, right? But you cannot do it for very huge scale. Here the accuracy would be very, very high, but this could not be ideal. If you have very less data or maybe mediocre data, in that case maybe you can do it, but this is not an ideal situation, right? The second thing is SME. So again, it's a manual way only. Expert is doing that. You are like hiring some intern and all for doing this specific thing, or some SME just do it for doing this thing, or like so many people are working in parallel, then this process could be faster. But again, this human annotation is not an ideal thing for the bigger data set. So the last thing is the LLM synthetic data. Means here to the LLM only you can give some instruction. Not instruction, I would say instruction will be the like confusing. Here to LLM only you can provide some prompt, okay, some guides, right, to the GPT kind of to GPT model, to Cloud model, right? So those model only can prepare your instruction data set. Means let's say you have a plain text. This text you are feeding to your GPT model and you are saying, can you prepare some question and answer from this particular text? GPT model will do it for you. So this is the one of the way, and company is following this specific way. Like they can generate a LLM synthetic data. Now guys, the next thing is, let's say if you have a data in this way, okay, but how the LLM will look into the data? Okay, means it will be like this: instruction, then input, and then output, right? Separate one, like we are having in the machine learning. As I told you, this is a supervised learning, right? Supervised. Why it is a supervised? Because we have a human curated output over here. But actually this is the language modeling. Language modeling means we are doing a next token prediction. Okay, so at the end we'll have to format this data in such a way that so that LLM can perform the next token prediction, right? So let's say this is my data, instruction, input, and output. So here you will be formatting your data in this way. So here is the instruction, then this is the input, right? And here you can see the response, guys. Getting my point? So here, guys, the native, right? The native role or the native behavior of the LLM to predict the next token only, right? So because it is a language modeling, the native behavior of the LLM to perform the next token prediction. So for sure, in whatever way we have a data, at the end we'll have to prepare a data in such a way that model can perform the next token prediction. So let's say we have instruction, input, and output. So for sure this is a supervised data because we have a label over here, but at the end we'll feed the model in this specific format. Okay, means input and instruction what will be there along with the responses, and model is going to be learned from this specific responses. I hope this is getting clear. Now let's see why this kind of tuning is required, why instruction tuning is required. Then we'll move to the practical. Now guys, let's understand why this instruction fine tuning is required. Let's take a look onto it. So here I written a base LLM like Llama, Falcon, GPT, or any LLM model. It only knows how to predict the next token. Okay. So I written over here. This means it understands the pattern only, pattern of the data, and based on the pattern only, it's going to be decide what will come next. Okay, next token or sentence prediction. So here is the example. You can see the example. We have an input. Metformin is used for. So this will complete the text. The output will be the treatment of type 2 diabetes mellitus. Okay, this is fine. But guys, if we are giving this kind of prompt to the model, like explain this, summarize this, write this, translate it, or what it is, right? So in this case, the model is going to be fail, means model will not generate the appropriate answer in a model will not generate a answer in a natural language, like how we human are talking, right? So that's why guys, the instruction fine tuning is required, and that was the like successful mantra behind the Chat GPT, right? How Chat GPT is giving the human curated answer, right? Human compatible answer because of this instruction fine tuning. So let's say yeah, here is example. If you will ask the model, write 3 points on metformin mechanism, so it might respond with something like this: write 3 point on metformin mechanism is request. Means it will just predict the next token instead of giving the 3 bullet point or 3 points. Okay, now because of this, right, because if we want a instruction like a structure answer, or if we want a relevant answer, right, if we want an answer in a human curated form, for that only this instruction fine tuning will be required. So here I written, so the conclusion is to teach the model the meaning and purpose of different prompts. Okay, so for the different prompts, we perform this instruction fine tuning. Now in the instruction fine tuning, how the data will look like, as you know, right? And what will be the result? So result could be anything, whatever user is asking. So I hope you understood why this instruction fine tuning is required. Now, without wasting a time, let's start with the practical. Now guys, let's start with the practical of the instruction fine tuning. So in this IPYNB file, I kept the entire code. Now in the previous video, I have shown you the practical of the non-instruction fine tuning. This entire code is already available on my YouTube channel. Please go and check the description of the previous video. You will get the link of this GitHub. Okay. Now in the previous video, guys, I have used this particular data matformin.pdf. So inside this PDF, I am just having one single page. Okay, but in the real time, the data could be very huge. Now guys, this was the non-instructional data, means the plain text. So I trained my model on top of this data. But in this video, we required the instruction data set, means we required the question, means the instruction and the corresponding responses. Okay, so I already created a data. I will show you in some time, right? Now over here, guys, I'm going to use the same model which I trained in the previous video. Okay, so what is my ideology over here? Let me talk about that what I want to teach you. So let's say we have one pre-trained model. Okay, so we took the Llama model. This is from the Meta. Now I got a problem statement that okay, I have to fine tune this model for some pharma data, right? So I downloaded this model, this pre-trained model, which was this one, Tiny Llama 1.1 intermediate step 1431K3T. Okay, this model is a quite small, that's why I have used it. Otherwise you can use any sort of a model if you have a good infrastructure. Now guys, I took a pre-trained model, I trained it. Okay, I performed the non-instruction fine tuning on plain text. Okay, now why did I perform it? So that I can teach my model the specific terminology. Okay, I can make my model basically this farmer ready. Now I will teach my model to follow the instruction. Okay, now what I'll do, I will do the instruction fine tuning, okay, on instruction data set. So guys, I have a data set, the plain text and all. I taught my model basically the language, the tone and all, everything. Now I will take this instruction data set and I will teach my model how to respond with respect to the different questions. Okay, then in the next video I will discuss the preference alignment. So based on the user preference, okay, which response needs to be picked up. So the next video I will upload with respect to this preference alignment. So as of now we are over here. I hope you got it. So guys, when I was training this model, right, so I already saved this model. So let me show you. So I already saved this model under this directory. You can check with my previous video. Okay, I shown you over there. And what I did after that, I zipped the model. Okay, and I downloaded that so that I can use it anytime. So here what I'm doing, I'm going to be basically unzip this file, this tiny LoRa.zip file, and then I will load my previously trained model. So first of all, let me load the tokenizer. I'm going to be execute this one. This is perfect. I think you are able to understand it clearly. Now let me run this. Okay, let me import all the necessary libraries. So here I think you are already familiar with all these libraries. Okay, now what I'm doing, guys, I'm going to be load the tokenizer. Tokenizer is very much required to perform the tokens, to get a tokens, okay, and the token ID with respect to the data. Now here what I'm doing, guys, I'm going to be unzip the model. See, here is my model, this one. After unzipping it, I will get like this one. This is my folder. I already run it, that's why I'm getting it. But if you are running it first time, you will means if you have this zip and basically if you will run it, then you will only get this checkpoint, right? So I'm going to be executed and see, after unzipping it, I'm getting this checkpoint -5. Okay, now guys, I got my model. Now let me load my model. So this is my model path. So what I'm doing, I'm passing it to this particular method, auto model for causal LM from pre-train, and here I'm passing my model path, okay, and device map is equal to auto. So I got my non-instructional model, right? Now what I can do, guys, after loading this model, so it might take some time if you are doing it first time. Now I am giving my prompt. This is my prompt: clinical trials demonstrate that whatever, right? Now what it will do, it will try to predict the future tokens. Okay, so it is not any instruction, it is not a specific question, it's just a simple sentence. Okay, and it will try to complete this sentence. So here's my prompt. First I will tokenize it, then I will pass my input. Okay, and these are the other parameter. I will discuss this parameter, it's very easy to understand. So how many max token would be there in the output. Temperature means whether my output will be creative or not. Okay, top P is also belonging to the same thing, right? So this parameter will discuss in the upcoming session. I will discuss some more theoretical, more like a mathematical point. Okay, so there we can talk about it, or else we'll discuss any sort of a API, right? OpenAI API, Cloud API, and there also basically we'll get this parameter, and for sure we can discuss. Now here I got the output. See, let me show you the output. So first we'll decode it, and after the decode, see, you will get the output. See, clinical trial demonstrate that combine atorvastatin with ezetimibe is a safe and effective to treatment of the like cholesterol. Okay, so like these are some pharma related terms, some disease specific term, even I am not familiar with it. So see, it is able to generate the response, right? Now what I'll do, guys, so here first of all let me show you how the instruction data set look like, and then I will take the same model, this non-instructional model, and then we'll try to perform the fine tuning. Okay, so to just give you the demonstration, see what I did, I'm loading this pre-built dataset, inbuilt dataset from the Hugging Face itself. It is already available inside this repository, AMOD repository, and the dataset name is this mental health counseling conversation, right? So once I load it, guys, see, I'll get the data inside this variable, dataset variable. Okay, now here if I can show you the data, see this data. Okay, is dataset. So let me write over here dataset. So I got the dataset. Now inside the dataset, I just have two columns, context and the responses. Okay, and how many rows we have? We have 3, 5, 1, 2 rows, right? Now I already downloaded this dataset just to showcase you. I downloaded in both format. In any format, basically you can keep the data. So this is a CSV format. Let me show you the CSV first. Okay, so inside this CSV you will get the context and the responses, right? So as I told you, this instruction fine tuning data set, it could be available in any sort of a format. Even I given you the example over here. So instruction input response, instruction context answer, user assistant, system user assistant, context and response. So inside this data set, which is already available over the Hugging Face. Okay, so inside this data set, basically you will get two columns. One is the context and second is the responses. Now see, the same data set basically I saved in the JSON format also. So yes, for sure you can keep it in both a format, right? Now what I'm doing here, so I loaded the data set. Now I am going to be formatted. So here basically I will be having my question, means this context is nothing, it is a question. This response is nothing, it is an answer. Right now I'm going to be combine both, and after that I'm keeping inside this text column. So let me execute it. So after executing it, guys, see what I'm doing, I'm mapping my entire dataset.map. Okay, and here I'm mapping my function. My function name is this format row. Okay, so once I'll do it, guys, I'll be getting my formatted dataset. Let me show you. So here is my context, this is my responses, and this is my text. Okay, so see over here. So instruction, what is the instruction? INST. Okay, it is a instruction. So this is the instruction. I am going through this, that, right? And then with respect to this instruction, here you can see the final responses. Okay, so what I did, guys, I formatted my dataset. Means either I can keep this context and response, okay, or I can keep it like this, instruction and this slash instruction. So instruction is only representing the question, and this slash instruction is representing to the answer, right? Now over here, instead of writing this instruction and question, I can simply write this context, means hash context, okay, or like this context and then response, right? Let me show you how I can keep it. So you can keep like this. So let's say here is your context and this is your response. Now whatever text column you will get, so whatever text column you will get like this. Means instead of the instruction you will be having the context, and then instead of the slash instruction you will be having the responses. Okay, in any sort of a form you can keep it, but over here what I wanted to show you that I have to pass my data as a final string only. Okay, this context and responses. Now what I did over here, see, I created a data frame of this data set, the data set which I loaded. Now see context and responses, you will get the context and responses under this data frame. Okay, then what I did, I just saved it. So here I already shown you this file, right? So I can basically load the data from the Hugging Face, I can save it in my local, or else if I have a data in my local, the CSV data and all whatever, right, I can simply keep it over the Hugging Face. I can compatible into the, I can create a compatible data set, okay, with respect to this Hugging Face. Everything is possible, right? So see, I have converted into the JSON, I converted into the CSV, and both way it is possible. I hope this entire thing is clear. So this is just, guys, this is just a this is just a demonstration that how the instruction data look like, okay, and how to format it for the training. Now in my case, in this particular practical, I am going to use my own data set. Means I'm not going to be use any pre-built data set over here. I will be using this particular data. See, let me show you this CSV. So under the CSV, basically you will only get 5 to 6 rows. See how many rows is there. I just have 1, then 2, then 3, then 4 and 5. Okay, only 5 row. Now I have an instruction. Okay, this is the output of it. Then again instruction, output of it, instruction, output of it. Now instruction, now this is the input, and here you can see the output of it. Then instruction, here you can see the input, and this is the output, right? So guys, you can read this data, you can analyze this data. On top of this data only, we are going to perform the training. Okay, we are going to perform the fine tuning. Now guys, here what I shown you how the pre-built data set look like. It could be in any sort of a like there could be any sort of a column, right? And here what we are doing now, guys, we are going to be load our own data set. This data set actually I created by myself manually. Okay, you can create it using the LLM, you can take a help of any SME, subject matter expertise, right? And you can generate this instruction data set. Now how ChatGPT has done that? So ChatGPT actually took the conversational data set. So conversational data set from the Reddit, from the Quora, from the GitHub, from the different places. Okay, but if you are doing for our domain specific problem statement, in that case we only have to create this data set. Okay, so I kept the data in both formats, CSV and jsonl. In the real time also it could be in any sort of a format. Okay, now I'm going to be loaded in a CSV format. So let's load it and perform the formatting. Now guys, I loaded my CSV data over here with this function load data. Then I'm passing this parameter CSV, then I'm passing my file path, okay, and then I'm writing split is equal to train. Means whatever data I'm going to be load over here, it will be a train one. Now inside the data set you can see we have 3 column: instruction, input and output. I can show you over here, this is my data set which I am using. Okay, now what I'll do, so after that guys, I will format it as a single string. As I told you, whatever data goes to the LLM, okay, it goes to as a single string, right? So let me run it, let me execute it. See, if you will see this formatting prompt, so we have an instruction, right? Instruction will come over here, then we have an input, okay, the example will come over here, and then response. Okay, so example input will come over here, then response, then example output will come over here. Okay, so here guys, if I will run it, and after running it I can map it. Okay, after mapping it, see inside my data set I am having 4 column now: instruction, input, output and text. Now this particular column, this text column, we are going to use it for the training. Now let me show you the first row. Over here you can see, so we have an instruction, then we have an input, and then we have corresponding responses. Okay, this is my responses. Now if you want to check with the CSV, now over here, see, check with the CSV. So this is my instruction, okay, and then in the input I don't have anything, it will be blank. Then I have an output, right? So this first row is going to be combined. Likewise the second row will be combined, third row will be combined, fourth row will be combined. Means first row will be combined, and that will become my one string. I will pass it to the LLM for training. Likewise the second row, likewise the third row, fourth row, and so on and so forth. Okay, I hope you got it. So guys, this is my data. I have formatted my data. Okay, so first row, second row, third row, fourth row, means whatever column we had over there, we just combine that and we'll be passing as a single string. And in that column, what we have our instruction and the responses of it. Now guys, see, this is the row which looks like this only. Over here you can see we don't have any sort of input is none, and then we just have the response. If the input would be there, then instead of the none, the actual data for the input will be passed over here. Now I'm going to be initiate my tokenizer. Okay, and now I'm going to be tokenize my data. So after tokenization, guys, see here I'm going to tokenize my data, means I'm passing my single example, my first row. Okay, now I'm taking the text from there, means this particular value. Okay, then I'm going to be truncate is equal to true. If max length basically if it is going to be exceed to the max length, then we are going to be truncated. Okay, otherwise we are going to be pad it if it is less than this 512, right? Now here is one more line, token labels is equal to token input IDs dot copy. So why I am doing it? So as I told you, the behavior of the model, so the behavior of the model is to predict the next token. Okay, so by using this line, basically I am telling to my model, so whatever data you will get, whatever text you will get, this entire row. Okay, so you have to train yourself in such a way that you are going to predict the next token. This all the thing I already discussed in my previous video. There also I have used the same technique. At some of the places I have seen, what I have seen, guys, so they are going to be mask the value till the responses. Okay, so till the responses they are going to be mask the value, means model will get to know, okay, so this till here basically I have an instruction, I have a question, and after that my response is coming. So how I will mask the value till response, means this particular value I can put any special toggle, like let's say I can put -100 over here. So here to here whatever token is going to be create, so for those token all the value will be -100 and the actual token will be assigned from here itself. Okay, actual token will be assigned from here itself. So this kind of technique also I have seen, right? So just to teach the responses to the model, we take this kind of we basically go ahead with this kind of technique also, right? But yeah, this is very effective, means we can entirely copy this input ID to the labels. What does it mean? Means I'm not going to be mask anything. Model from this particular text, model will learn how to predict the next token, right? So here is the all the thing is done. Now what I'm doing, guys, I'm going to be load my I'm going to be basically load the model as a LoRa model. So from the PEFT I have used this LoRa config, then get PEFT model, then task type. Now here whatever basically parameter I have used, you can see the description of it. So task type means it's a causal LLM, means the next value prediction, next token prediction. Now here R is representing to the rank, so this could be the rank. Okay, control to enable parameter size. Now here LoRa alpha, it's a scaling factor, so the value will be between this one. So balance adaptation strength. Now LoRa dropout, so dropout probability 0.5, so it's a regularization value. Target module, which layer to tune, so I want to tune this query and the value. Trade-off between cost and quality, means you can select the other layer also. We have a key query value, right? So you can select the different layer which is remaining, the next one. Okay, then biases fine tuning none, keep simple. Okay, so over here guys, we are going to be mention this parameter, but under this particular class LoRa config, you will find out so many parameter. So maybe after discussing the mathematics of this LoRa, we can talk about it, right? So here is my LoRa configuration, guys. Now what I will do, I will write get PEFT model. So here I will pass my non-instructional model which I trained in my previous video, and here I am passing my LoRa configuration. Okay, now I will be getting my LoRa model. See here I got the LoRa model. Now what I'm doing, I'm going to be define my training argument. So tiny llama instruction, here I will be getting my instruction model. For 3 number of epoch I'm going to be train it. Okay, per device train batch size, means how many batch in how many batch we are passing a data. Gradient accumulation step, so at what all step we are going to be calculate the gradient. Learning rate regarding the optimizer, it's a precision value. Logging step, at which step we are going to be log the value. Save total limit. Okay, now repeat report to none, means we are not going to be capture any sort of a matrices anywhere on any platform. So this is my all the argument, guys. Now what I'll do, I'll call this train method. To this train method I'll pass my model, I'll pass my argument, I'll pass my tokenization, right? Now my trainer is ready. Now what I'll do, I'll call this train. Okay, so here guys, see my model is getting trained on top of this data set. Now my model got trained. Now here actually you will get the model. See tiny llama instruction, this is my model. Okay, and under this you can see I have a checkpoint 3, and see my model got saved over here, adapter model dot save tensor, right? Now let me execute it. See, this is a model path. Now after that what I can do, I can load my instruction model. Now here guys, see this is my instruction model. Now I can give this kind of question to my model, explain the mechanism of the action of metformin, right? So earlier guys, I was maybe I cannot give this kind of question to my model, it will definitely hallucinate. Okay, we'll compare that, don't worry. But guys, now after the instruction fine tuning, we can give this kind of question where, see, my data set is very small, I just train it for very simple epoch. Okay, my model is also very small one, so it might not predict correctly. But if you are doing it on a full scale with a good model, with a good data set, with a huge data set, okay, that definitely this technique will work. So here is my prompt. Now what I'll do, I'll tokenize the prompt, I'll pass it over here, means I'll pass all the tokens over here. Okay, now let me take the output. So here guys, you can see the output. So what output is generating? Clinical trials demonstrate that combine atrovestine with azitimb is a safe and effective for treatment of the hypercholesterol. Okay, so guys, here I ask, why explain the mechanism of the action of the metformin. So see, it is going to be explain everything, right? So it is going to be explain everything in the normal human tone. Okay, now over here guys, you can see, so this is all the data which I have. Now guys, I load the CSV data. You can load the data in the form of JSON also. Okay, and this is the pre-built data set which I took from the Hugging Face, means I shown you how to load it from the Hugging Face, and even I shown you how you can save it, and after saving it, anytime you can load it. Okay, or else if you will get the data in CSV and jsonl, then from there you can easily load everything I have shown over here. Now I hope guys this thing is clear. Now let me show you one more thing. I was telling you that basically before the responses, okay, we can mask the value so that model can easily understand my response is getting started from here. So I took one code over here. Let me show you. So see what is happening over here. See, we are taking a data set. Okay, we are loading a data set, we are formatting a data set. After that we are passing it to the tokenizer. Okay, the tokenization and all, everything is done. See, here basically I'm going to be initialize my tokenizer. Now see, I'm getting my text. Okay, now after that guys, see, I'm getting my input IDs, means my tokens. Now here I am writing response marker. So this is my response marker. Now wherever I will find out this response, or from wherever the response is going to be, start response, answer, whatever you can say. Now over here what I'm doing, so I'm going to be mark it. Okay, I'm going to be mark it with this. See, till the response, actually I'm going to be marked with this -100. Okay, so till the response, actually I'm going to be mark it with -100 with this special token, and after that the normal token would be there. So what does it mean? The mean is very simple. See, here I have written clone labels and mask out everything before responses. So the meaning is very simple. My model will be able to discriminate between the instruction as well as the responses. It will get to know, okay, till here means this is a special token, means this is my input, or like my instruction, and after that my actual response is getting started. Okay, so both training you can do, you can try out with this one as well as the previous one. Okay, you can check which one is giving you the effective result. According to me, the previous one is a good one, because here there actually my model is learning onto the my model is iterating onto the entire string. Okay, the entire row, right? Text, the instruction, input, and this responses. Okay, now here till response we are masking, and after that only we are allowing to model to learn through some tokens, right? So yes, I have like written this logic over here. You can go through with it. I have seen in many like places people are following that, so that's why I given you this particular like solution as well. Okay, you can try it. Here is the entire code. Now guys, so I kept some question. Okay, and what I'm doing over here, I'm going to be check with my non-instruction and the instruction model what is going to be the answer, right? So I have both model, instruction and the non-instruction. So see, this is my question. Now what I'm doing, I'm iterating over the questions. Okay, now I'm tokenizing it, and after tokenizing it guys, I'm passing to the non-instructional model. I'm generating output and then printing the output. Now here what I'm doing, I'm going to be load the tokenization model. Sorry, I'm going to be load the tokenizer, then I'm loading the instruction model. Okay, and then I'm going to be perform the then I'm going to be generate the answer with the instruction based model. Okay, so here I'm going to be generate the answer with the non-instruction, here I'm going to be generate the answer with the instruction. So you will be able to understand. Okay, so if I'm asking this kind of question like explain this, summarize this, what is this, what is that, so instruction model will be able to perform good compared to the non-instruction model. So that's why guys, instruction fine tuning is required. See, my data set is very small, my model is also very small, so it might not give the correct answer. But if you are doing it really, first teach your model on your domain specific data set, on your PDF text and all, and later on perform some instruction tuning. It will work well, guys. It is proven technique. Okay, ChatGPT also did the same thing, right? First they have trained the entire data. First they have trained on the entire internet data, the self-supervised learning, and then after that they have trained it on a question answering task from the Reddit, from the Hugging Face, sorry, from the like different forum like GitHub, Stack Overflow, and all, right? So let's run it and let's see what is going to be answer. So here it can predict it. See, the answer, explain the mechanism of metformin. So it is saying explain the metformin is drug. Fine. Now here, okay, expect output, test case. Okay. Now here it is saying summarize how mRNA. So guys, it is predicting something, right? Some garbage thing. Okay, you can try out from your end, you can check, right? You can take some more data and then basically again you can retrain and check that out, right? I took the very specific question, just 4 to 5 row, guys. With respect to LLM is nothing. Just take some good data set, retrain your model, okay, on the instruction data set and check. Okay, means first take the base model, check with the non-instructional data, means some PDF and all, train it, and then ask the question, and then again do one thing, create some instruction data, give your model, so model will learn how to follow this prompt and all, and then again ask the question to your model and check, okay, in which way it is performing well, in the instruction way or in the non-instruction way, right? So now let me show you that what all thing you're gonna learn inside this particular video, and then step by step, one by one, we'll implement all those things. So here I kept the complete points, guys. So we'll learn about the preference alignment or preference training. Then we'll understand why do we do preference alignment, means why it is required. Then we'll see the example, dataset example, like how the dataset look like. If I have to do the preference alignment, then what kind of data I will have to create. Then we'll see techniques for the preference alignment. So what all technique we have? We just know about the RLHF, that is called reinforcement learning through the human feedback. But that is not only one of the technique. We have a couple of other techniques. So definitely I will discuss onto it, and even I will show you the research paper. Then the very famous infamous technique for this preference alignment, that is called DPO training. So we'll understood about the DPO training. We'll see the mathematical formula. I'm not going to show you the complete mathematical intuition along with the derivation and all. I will just focus on the formula, and we'll discuss about that formula. Okay. Then we'll see the practical implementation with the DPO itself. So whatever model I had, means whatever model I trained in my previous class, the instruction fine-tune model, I'm going to take a same model, and on top of it I will perform the DPO, that is called direct preference optimization. Then during the practical I will show you the LoRa adapter, means how you can use the LoRa adapter. Why you should not directly implement the LoRa, okay, if you are going to be use the already fine-tuned model. Okay, how to use the LoRa over there, definitely I'll show you. That comes under this LoRa adapter. So yes, we are going to discuss all this point throughout this tutorial. Now after this tutorial, guys, you will be like become a champion in the preference alignment, and you can basically fine tune, okay, you can train any sort of a model on top of the preference data. Now let's start with the theory, then I will come to the practical, guys. Now here, guys, I created a step-by-step notes for all of you so that you can refer it later and you can revise your concept. Now before starting this thing, let me show you the notes from the previous session. So for that, I have created one repository with the name of this complete LLM fine-tuning. There only I am uploading all the notes and all everything. Now where you will get a link of this repository, so you will get inside the description of the video. Okay. So here I created a repository for the LLM fine-tuning 14, for the 15 and 16. So the 16 basically it's a current video. Okay. Now I likewise I will create for the other basically video also. I'm getting so many requests, sir, please upload all the notes and all. So definitely I'll update this particular repository. Okay. Now guys, if you will go and check with the previous repository or with the previous notes, right? So here it is. Let me show you. So see all the files and all everything I kept. Handwritten notes is there. IPYNB file is there, CSV file, JSON file, even the GIF file, model GIF file also I kept, right? So you can directly download it and you can start your practice. So guys, this was the handwritten notes. Now here I discuss some fundamental thing. So I discuss about the LLM training process. So the first step of the LLM training process is called the unsupervised pre-training or self-supervised training. So here we get the foundational model, okay, at this particular stage. So we are not going to perform this particular thing from our end, right? We are taking any foundational model from the Hugging Face or from any other places. Now our aim to perform the fine tuning, okay? So regarding the fine tuning, I shown you the supervised fine tuning. So I shown you two way, one with respect to the non-instruction data, and the second with respect to the instruction data, okay? The instruction data one is specifically called the supervised fine tuning, but if we have non-instruction data, in that case also we can fine tune the model. I shown you each and everything. You can refer the previous video. Now in this video we'll discuss about the third point, okay, preference based alignment or training, right? So these are three main stage of any LLM training, right? And now we are going to discuss this third one, and after this after this video you will find out video on top of the different framework, okay? Because in this video we'll complete the third stage, the last stage of the LLM training. Now guys, let's start with the theory of the LLM based alignment or preference based alignment or preference based training. So guys, to align or train a model with a human expectation or with a human preferred data is called preference alignment or preference training. So this particular technique was introduced by the OpenAI in Instruct GPT paper. Don't worry, in some time I will show you that particular paper, and definitely you can refer that. Now why we do it? We do it to get a safe, helpful and the honest model. Maybe you're not getting couple of things just by reading this particular definition, but you will get once I will show you the different example. So here I kept one example. Just read out this statement. So user is asking one question to the model. So the question is very simple. How do I lose my weight? Okay. How do I lose weight faster? Something like that. So I have a fine-tune model. Let's say this is the instruction fine-tune model. Now it is answering. It's a simple thing. What you have to do, you just have to stop eating, right? Just stop the eating. Give me a moment. I think now it's fine. Yeah. So just stop eating so much. Now you can see the answer is correct, but it is rude, it is dismissive, and there is no explanation. Means it is not aligned with the human expectation. If ChatGPT is giving you this kind of answer, maybe you will not be satisfied. The answer should be according to the human expectation, right? So let's say this is the output from the instruction fine-tune model. Now just look into the one more response, right? Now just by seeing this response you will be more happy. And nowadays from the ChatGPT or from any basically large language model, we are getting this kind of output because the model further have been trained on a human preference data, okay? Now just look into the another answer. Now let's suppose we have one more model which have been trained on a preference based data. So the answer is safe weight loss generally happen gradually, okay? You can start with a balanced meal, regular movement, adequate sleep and hydration. If you have medical condition, it's best to get a personalized plan from a professional. I can help you with the simple step if you want. Now guys, just look into the difference, right, between this answer, this particular answer and this answer. So if you want to generate this kind of answer, right, so maybe you will have to take one more step with respect to your LLM training. You will have to perform the RLHF, RLAIF, that is called reinforcement learning through AI of generated feedback, or you will have to perform the DPO, that is called direct preference optimization. Now first two technique, RLHF and RLAIF, it is based on the reinforcement learning. And the second technique, DPO, it is a simple supervised training, okay? So yes, definitely we'll discuss. Now here you can see in the second one, in the second output, you can see the answer is having a correct tone. It is a respectful, right? And it gives the proper explanation with the like it is a more helpful answer. Okay, it's a more human aligned answer. So that's why guys, I was saying this preference training or preference alignment is a very important part of the LLM training. Now coming to a couple of more example. So here I kept one more line. So after the preference based training, model does not just produce accurate answer, it behave according to the user preference. Okay, it behave according to the user intention. So that's a like key difference between a normal fine-tuned model or a aligned model like GPT-4, GPT-5, 5.1, 4.0, 4.1, whatever like latest and the state of art model you can see. Now why we do this preference training, guys? So this preference training we do to improve the safety and ethics of the model. We do it for generating the helpful answer, for the more polite answer. Okay, we teach the model so which can respond like a human, means which can response in whatever way the human wants. I kept one more example, maybe with that your understanding will be a bit more clear. So how I can lose 10 kg weight in 1 week? So if we have a normal trained model, so see how it is going to be generate answer. You can stop eating, drink only water, and take fat burner pills. This will reduce weight quickly. Okay, so just suppose this model basically it has not been trained on a human preferred data, right? Now here guys, you can see the another answer. Now another answer is rapid weight loss 10 kg in a week is unsafe. Okay, and it is medically harmful. A safer approach is just to lose 0.5 to 1 kg per week through balanced diet, hydration, and activity. If you have urgent concern, please consult with a doctor. Now guys, tell me which answer you will refer. So you will refer this particular answer or this particular answer, or which is a more ethical, which is a more safe answer. So definitely this answer is a more safer compared to this one. So in the human preference training, in the preference alignment, basically we teach to the model to behave like this. I hope you are getting my point now. Now we'll see the different technique, what are technique we have, and we'll look into the DPO formulas and all, and then we'll go for the practical, guys. Now guys, let's see the dataset example. Let's see how the data looks like for the preference training. So here I kept the example for all the three methods. The first one is for the non-instruction fine-tuning as well as the unsupervised pre-training. In both cases, the data will be the plain text. Okay. Now how the input and the output column will look like? So the output column will be the next token. Okay. And the continue word. So let's say this is my sentence. Now what is the next word of it? This is the next word. So this will be my output. Now see, this is my complete sentence. Okay, till oral. Now what is the next word? This is my next word. Now here you can see this is my complete sentence, right? Now what is the next word? This is the next word. So inside the non-instruction fine tuning or inside the unsupervised speed tuning, what we are doing, we are predicting a next word. So the next word will be inside the output column. Okay. Now how to decide the length of this input and output? So for every model we have one specific context length. Okay, so according to that we can decide, right? Now the second is the instruction fine tuning. Now in the instruction fine tuning we will be having 3 column or sometime you will only get 2 column. Okay, so the first column is the instruction, the second is the input, and the third is the response. In this particular format you will get a data, or else the data would be like this: input, called context, and the answer. Or the data might be like this: user and the assistant. Okay, or sometime you will see context and the response. Means the moral of the story is we will be having one input column and the corresponding output column. Okay, then how to format this data and how to utilize it for training the model. If you want to know everything in detail, then please go and check with my previous video, right? Now how the data look like for the preference training? That's the main agenda of this video. So inside for the preference based training, guys, you will find out three main column, right? One is a prompt, second is a chooser, and the third is a reject. Now this two is very important. choose, right, which one is going to be select, and which one is going to be rejected. Now let me show you some real example from the Hugging Face itself. So here is a data from this Anthropic. So Anthropic has uploaded one data. Okay, the repository itself is Anthropic, and the data set is called the RLHF. Okay. Now here inside this particular data, you will find out two column only. The first is a chosen and the second is a rejected, right? Now you can see the another data. So inside, see this data, basically it is available inside this ARGILLA repository, ARGILLA, right? So the data set name is ultra feedback binarized preference clean data. Now inside this particular data also, you will find out two main column. First is the rejected, and the second column will be the chosen, okay, along with the given prompt, right? Now here is a third example. So this is available inside this XinLai repository. So the dataset name is math step DPO 10K. Now inside this particular repository also, inside this dataset also, you will find out two main column. The first one will be the chosen, okay, with respect to the particular prompt, and the second column will be the rejected. Okay, so see here is a rejected. So choose and reject, right? Select or reject. This will be the two main column inside any preference data set, right? Choose means which one we are going to be select, and reject means which one we are going to reject, right? I hope this thing is clear. Now let's see the technique, guys, and then what I'll do after that, I'll show you the DPO formula, okay, and then we'll jump to the practical. Now guys, let's see the technique for the preference alignment. So the very infamous technique that is called RLHF, reinforcement learning through human feedback. The second technique is RLAIF, reinforcement learning through AI generated feedback. The third is DPO, direct preference optimization. Now these are the algorithm KTO, PPO, IPO. It's a reinforcement based algorithm to implement this RLHF or RLIF. In RLAIF also we use this particular algorithm. Okay, so what's the full form of this algorithm, just for the general knowledge? So KTO is called the Kahneman-Tversky optimization. PPO stand for proximal policy optimization, and this IPO stand for implicit preference optimization. Now this is a very famous technique, guys. Even OpenAI is also revealed that they have used this particular technique initially for the reward modeling. Okay, PPO, proximal policy optimization. It is a reinforcement based technique. Okay, reinforcement, it's a like reinforcement learning algorithm. Now the technique is RLHF. What is the core idea? The core idea to train a reward model using the human feedback. Now what kind of data we were using there? Ranked responses, okay, which was ranked by the human. Example, OpenAI Instruct GPT. So this is a research paper. One model basically was released by the OpenAI. Regarding that model, I will show you the research paper, this OpenAI Instruct GPT. There also you will see the use of this RLHF technique, okay, through this PPO. The second technique is called RLAIF. This was introduced by the Anthropic. Okay, so inside the RLAIF, you will get the AI generated feedback. So human generated feedback was not very scalable idea. Means how many feedback can be annotated by the human, right? Maybe 1 lakh, 2 lakh, right? But if we have to make it scalable, then how we can do it? So there they have introduced this RLAIF, where human is not giving a preference. Actually, we are taking that particular preference from the AI itself. Okay, so this was discussed inside this research paper. I'll show you in some time. The third technique, and very popular and in demand technique right now, that is called direct optimization policy, okay, using the preference pair. The full form of it, direct preference optimization. Now guys, this is not a reinforcement based training, okay, reinforcement based learning. So here we are not going to use reinforcement learning. This is a simple supervised learning. Okay, simple supervised learning means we just have input, and in the other column we will be having the output. That's it, guys. Okay, so chosen and the rejected, that's it, right? So nowadays we are using this particular technique only. Now let me show you the research paper regarding each and everything. So guys, I will attach all this research paper in the description. So this is the first one. The research paper name is Training Language Model to Follow Instruction with the Human Feedback. So just check out with this particular research paper. You will get so many detail over here. And this research paper was published by the OpenAI. It's a very good research paper on top of the RLHF. Just read the instruction at least and the couple of headings. Okay, you will understand. See here, I was saying now. They have used the PPO technique, proximal policy optimization. So initially for the RLHF, they have used the PPO technique. Okay, so just read out this research paper now. The second one is the direct preference optimization DPO technique. It is also very famous technique, and it was introduced by the Stanford University, right? So just look into this particular research paper. You will get the complete details. See here, this particular research was published by the Stanford University. Now here you will see the Indian, also one Indian, Archit Sharma. Now the couple of other person, right? So just see, it was released in 2024. And just read out the abstract at least. Okay, you will get the complete detail of what is a DPO and how we can implement that. Now the third technique, which is called RLAIF, right? So it was inspired from the RLHF only. The difference is human is not going to be annotate anything now. Like only AI will do that. So just check out with this particular research paper. It is a very good research paper. You will get like very good knowledge through this research paper. Okay, and this was published in 24 last year itself. It's a very latest research. Now here also like you will find out so many contributor. Okay, so Abhinav Rastogi and Sushant Prakash is one of the guy, right, who contribute inside this particular research paper, right? So just read it. You will get the complete detail of the reward modeling and the differences between the RLAIF and the RLHF. Now guys, let's look into the DPO. Okay, because see, we are not going to use the RLHF technique, RLAIF technique as of now. Maybe I'll show you in the future, but that is deprecated now. People are using DPO, which is like very simpler, okay, and simple to use. So I will show you the formula of it, formula of the DPO, and then I will go for the basically practical. Okay, so let's start with that. So guys, here is a DPO training loss intuition. So it's a loss function. So based on this loss function, my model is going to be trained. Okay. Now guys, you know about the supervised learning. So in the supervised learning, we have input, then we have a output. Okay. Now this output, basically it is called the actual output, which we generally demonstrate with the Y. And then we are going to be predict, right, something from the model that is called Y hat. So we check the differences between this Y and the Y hat, and we try to minimize. See, this differences actually it is called the loss. Okay, and we try to minimize this particular loss, right? So that's the overall idea behind the supervised learning. If you don't know about it, you can learn about the linear regression. You can learn about the artificial neural network. Okay, there you can learn about this particular concept. Now using see, this is the loss function, and using this particular loss function only we are going to train our model. Now let's try to understand this formula. Now why we are understanding that? So let's say if someone is going to ask you in an interview, right? So how did you train, how did you like perform the training, this preference training, right? So you can say I perform using this DPO, and inside the DPO basically we are using this loss function to train my model. Okay, it's a supervised learning only. So inside this formula we have so many terms, but it is not very like complicated. It seems complicated, but it is not. Let's try to understand it. Okay, so here you can see we have this pi theta, pi reference. So pi theta actually it's a preference aligned model, okay, which is trained. Now this pi reference is what? This pi reference actually it's a reference model. So it's a instruction tune model, okay, which comes before the preference alignment model. Okay, so pi theta and pi reference is clear. Now pi this y plus is what? This y plus actually prefer response, means the chosen response, okay, with respect to what? With respect to this prompt, x prompt. Okay, now here see, this is like my reference alignment model. Okay, and here basically we are passing this this is my preferred response with respect to this prompt. Okay, now here is my reference model, right, and here is what? Here is my preferred response with respect to this particular prompt, right? Now similar to that you can see over here. So the model is there, right? Y minus means what? Y minus means rejected response with respect to this prompt. Okay, I hope you understood it. Now we have a couple of more terms. So we have this sigmoid. Okay, now apart from that sigmoid, you will find out this beta. Okay, and now you will find out this minus e, right? This minus e is nothing, it's a symbol. Okay, minus e means what? Expected, right? What we are expecting? We are expecting this term should be minimum. Okay, and this term should be the maximum one. That's it, guys. Okay, just a symbol, nothing else, right? Now let's try to understand one by one. I just kept I just broke everything over here. So a log pi theta, okay, y plus with respect to this x, and then pi reference, the reference model, okay, y plus with respect to this x. So what does mean? The meaning is how much more does your model prefer the chosen answer compared to the reference model. Okay, so here is what, here is my basically preferred model, and here is my reference model. So with respect to this reference model means my supervised trained model, I'm checking how this preference model is behaving, right? Now similar with respect to this rejected prom also. Okay, so the selected prom as well as the rejected prom. Now what we'll see the differences. So chosen improvement, okay, and the rejected improvement. So if it is going to be positive, means my model is aligning to this chosen prompt, okay, the chosen output. Now here sigmoid, what it is doing? So you know the value of the sigmoid, it is between the 0 to 1, right? So it is giving me a probability, okay, kind of probability score, right? Now here beta means what? Beta is a scaling factor. So if the beta is high, means we are enforcing model to we are enforcing model to align more to the chosen. Okay, if beta is low, means the rejected one, the model is more aligning to the rejected. Okay, the typical value of the beta between 0.1 to 0.5, right? And here I written the minus e, meaning what is the meaning? We want to minimize the negative, which means the maximize, we are going to be maximize the positive value. So here let's understand the meaning again. Let's take a quick revision. So this particular term with respect to the preferred response, okay, means the chosen response. So we have two model. This is my preference aligned model, this is my reference model. Okay, same with respect to the rejected response. So we are checking, right, how my, so here what we are checking, how much more does your model prefer the chosen answer compared to the reference model. Okay, so we are going to be compare with respect to this reference model. Then what we are doing, we are going to be scale it, right? And then we are going to be check the probability, right? We are just going to be compress the entire value between 0 to 1. That's it, guys, nothing else. Okay, and if the answer is positive, okay, we are getting more positive in like multiple epoch, we are training for the multiple epochs, and this result, the loss result is going to be positive, means my model is aligning to the chosen responses. That's it, guys. So I hope you understood it. Later on in a dedicated video, I will show you the derivation of it. Now one more thing, guys, before coming to the practical. So I kept a couple of more point with respect to this Instruct GPT paper. So this paper, just now I shown you this paper, right? Training language model to follow instruction with the human feedback. So this is the Instruct GPT research paper. Now regarding that, I kept a couple of point, few summarization, right? So here human was labeling the data, right? So whatever response we were generating to the model, human was ranking those things. Now using the PPO, basically we are going to be find out which is like more helpful, right? So this was a chat GPT style alignment, so which initially was done by the OpenAI. Okay, now on what all prompt, basically we are finding out, we were generating the output. So on top of the API user prompt, means whatever a user was writing, okay, through the API, okay, some question answer, right? Sorry, some public questions, basically those prompt was taken, and on top of that they have generated an answer from generated a multiple answer, and then human ranked those answer, right? So this is like some extra information, you can confirm it from this particular research paper. It is very good like to understand the to understand how they have initiated the RLHF technique. Okay, now let's move to the practical, guys, and after that basically I'll show you the comparison between all the model. Okay, and one more important concept with respect to the LoRA adapter. So here only we'll cover that part. So guys, we had the base model. If you remember, then I took the base model. This base model is also called the foundation model. Now here is my foundation model, my base model. So I fine-tune this model on top of the PDF data. and after that I got this particular model, non-instruction model. Now why we have done this thing? So that my model can understand the domain specific language, domain specific vocabulary. Okay, then I want to teach my model proper conversation. So what I did, I fine-tuned my model on top of the input and output data. Okay, means on instruction data. Okay, so what I got the instruction model. Now guys, I want to be train my model. Again, I fine tune my model on human feedback. Okay, so after that what I will get the preferenced model. So this is the aim for this particular video. I hope you got it. Now for that what I'm going to do, I'm going to load all the libraries. So I'm going to load the auto tokenizer, auto causal for LM, training argument trainer, LoRA config, get PEFT model task type, and load dataset. So I will teach you the meaning of each and every class, each and every function which I'm loading over here. So yeah, this is done. Now here is my base model. Now why I've written this base model here, so that I can load the tokenizer. Okay, because this tokenizer I will be using. So yes, the tokenizer is here, tokenizer is ready, and I think I already explained you the meaning of this pet token and this end of the sentence token. You can check out with the previous session itself, you will get the entire detail. Now what I'm doing guys, so I'm going to unzip my previous model, this tiny llama instruction.zip model. Now why I'm doing it, because I'm using a same model throughout this journey. Means I was having the foundation model, then the same model I train on the PDF data, I got this model. Then same model I train on the instruction data, I got this model. The same model I'm going to train on the human feedback data, and I will get my final preference model. Okay, so here what I'm doing, like when I trained my model in the previous class, so I saved that as a zip file. So this zip file is also available in the GitHub. You can check it out directly. Okay, or if you will train it, if you will train the model from scratch, okay, over here using this particular notebook, this IP1B file. So at the end you will get this particular model itself, this tiny llama hyphen instruction. Okay, then you can convert into the zip and you can save it anywhere. That's it. So guys, I have a model. I have already uploaded this particular model over here. You can see. Now let me unzip it. So after the unzipping it, what I will get this checkpoint 3. Okay, so this is my train checkpoint, instruction checkpoint. Let me load it. Let me take it inside the variable. Now I'm loading it. Okay, and I'm testing whether everything is working fine or not. So for that I kept one prompt. So explain the AI in improving the process of the drug discovery and the development in the pharmaceutical industry. So this is my prompt. Now this first what I'll do, I will convert into the tokens. Okay, and I'm mapping to my GPU. Now I will pass this token to this method. So instruction model dot generate, I'm passing the token. Along with that I'm passing some other parameter, like how many tokens I want in the final output, some other parameter with respect to some tweak, some creativity in the output. Okay, now repetition penalty means the token should not be repeat. So regarding that we can mention this particular score 1.1, and I think this score we can like write up to 2. You can check out the complete detail of it. Okay, so yeah, this is also one of the parameter. It will stop the redundancy of the token. Okay, so we'll get output. Let's see what output I'll be getting over here. So before the class, right before the class I was testing, and I already run it. Okay, if you are running it first time, then it might take some time. So here is the output. So explain how intervenient, this is the question. Now regarding that, see the answer is being generated. You can get some better answer. If you have much data, then definitely you will get some good answer, aligned answer itself. Now here this answer is also aligned, and it is with respect to my question. Now I want to perform the preference based learning. So for that guys, we are going to use this TRL module. So under this TRL module only you will get all the preference tuning based classes like DPO, like RLHF, like RLAIF. Okay, so different classes you will get under this particular module only. So let me install it. So the command is very simple, pip install -u TRL. You will get the latest version. Now after that, if you want to load a quantized model, so there is one more package, bits and bytes. So let me load, get this package also. Okay, now guys, after executing this two command, pip install -u trl and pip install -u bits and bytes, you always restart the kernel, otherwise you might get an error that this package is not visible. Okay, so let it install, and after completing this one, what I'll do, I'll restart the kernel. Okay, this is done. Now what I'm doing, I'm checking with the runtime. Now here you can see the restart session. Just click on this restart session. Okay, the kernel will automatically restart. See, right hand side, it is getting restarted. Now load this step again. Okay, because after restarting this will be gone. So yeah, everything is fine. Now guys, this module is installed, this bits and bytes is also installed. Now let's try to perform the DPO training. Now here I want to teach you one very important concept of the LoRA, guys. It is very important. I think most of the beginner and even the experienced person does this kind of mistake. So I don't want to repeat that mistake over here. Okay, and even I rectified that mistake in the previous solution also, and definitely I will highlight those part. So for this preference based learning, I'm using this DPO trainer. Okay, rest of the module will be same, which I already imported in the previous cell. So from the TRL itself, we are going to import this DPO trainer. If you are doing RLHF, or if you are using some if you are doing the RLHF, RLAIF, right? So from the TRL itself, you will be loading everything. Okay, so we are having this DPO trainer. Now what I'll do, so here is my base model, guys. Then this is my instruction checkpoint, right? So my model is available over here inside this particular checkpoint, the instruction model. Now after that, guys, you can see, so we are going to be load the data set. So here the data set plays a very important role. I will show you what kind of data I'm using and how I created that. Then I'm loading the tokenizer, and after that you can see we are assigning this end of the token to the padding token. Okay, so let me check what is happening, whether everything is ready or not. So yes, this is running, because see guys, we have a limited memory, so we might get some issue with respect to the memory and RAM. So better don't execute everything again and again, the harder step, otherwise you might face a issue in the collab. So yes, it is working fine. My model is still giving me a reply. Now TRL, with respect to the TRL in bits and bytes, I reloaded the environment. Now first of all, let me import all this statement. Okay, so after that, guys, what I'll do, I'll take the base model, I'll take the instruction point. Now here is my data set. So how the data set look like? So I already kept the data set over here, pharma preference underscore data.csv. This data could be available in CSV as well as in the JSON format. So I basically kept the CSV as of now, but you can load the same from the JSON file also. So how the data look like? See, here is the data. So inside the data, you will get the prompt. You will get the chosen one column. Okay, the second third column will be the rejected. So we are giving a prompt to the model, then we are generating a multiple answer. Now which answer is being selected and which answer is being rejected, so that particular information we have kept over here. I think you got this point. Now whenever we are passing a prompt to the model, okay, so model will generate something, so that this can be wrong, or this like can be the correct one. So initially I shown you like how the human annotated this entire labels and all, whether I have to choose it or reject it. Later on we have automated this task also, okay, on a very high scale. So this task have been automated by the LLM only. So we are giving certain instruction to the LLM, and based on that it is able to find out which is the chosen one and which is a rejected one. I hope you got it. So this type of data we required for what? For the training. Now here, guys, see, we are loading a base model. Okay, we are having the instruction checkpoint. Now we have a data set also. Now what I'm doing, I'm going to be perform the tokenization. So from the auto tokenizer, I am loading my base model. Okay, so it will come inside this particular variable, tokenizer variable. Then what I will do, guys, so after that, the same thing, you will have to assign the pad token. You will have to assign the US token, end of the sentence token, as a pad token, right? Now here we need to understand one very important concept. So we're talking about the PEFT module. Okay, so PEFT is giving us two different methods. So see, PEFT, we have a PEFT, right? So from the PEFT we are importing this PEFT model, and from the PEFT itself we are importing this get PEFT model. So guys, we need to understand the differences, okay, between this PEFT and get PEFT model, because it is very much important. So guys, I capped the complete intuition over my blackboard. So let's understand it one by one. So what we are doing, guys, as we know, we are having base model, then we are training it for the non-instruction model, then instruction model, then preference model. Okay. Now, how we are doing this training? So we have a base model. Now we are doing the LoRa based training, and we are getting a non-instruction model. Then again, we have a non-instruction model, and we are adding the LoRa adapter, LoRa layer, and we are getting an instruction model. Now here again we have an instruction model, okay, and we are adding the LoRa. We are means we will try to do the same one. We will add the LoRa, okay, and then we'll get the preference model. But guys, to be honest, this is not a good thing. This is not a good practice, and no one is following that. Okay. Now see over here what we are trying to do. We have a base model. We are connecting with our LoRa, okay, the LoRa adapter. Then base model LoRa. Then again in the instruction tuning, again one more LoRa. Then we have base model LoRa, and then again one more LoRa would be there if we are following the same step over here. So stack of the LoRa layer is not good. Stack of LoRa is not a good idea, guys, and that's a step I followed in my previous tutorial, right? And you were able to see the responses. It was not quite good. Why? Because the LoRa layer was getting stuck. Now if you don't know about the LoRa, don't worry. In the upcoming video I will explain you with complete detail, with a complete mathematical derivation and all. Okay, so don't worry about the LoRa, but let me give you the quick definition of it, what it is. So here I written LoRa is not a full layer. Okay, it's not a complete model, it's just a delta patch. Okay, so delta patch cannot be stacked, they must be merged before the next training. So what is this delta patch? This delta patch you can think in such a way. We have a weight, old weight. To this old weight, we are going to be attach some small matrix of weight, okay, and we'll get the new weight, okay, new weight, WEIGHT. Okay, so we are having the old weight. We are going to be attach it with the like some small weights. Okay, and now this particular patch, the small patch. Okay, it is only called the delta patch. Okay, so my LoRa is nothing. It's a small patch. It's a small weight which we are going to be attached on top of my old layers. Okay, and then what I will get? I will get my new weights. So here is a proper mechanism for it. Means this particular weight is being trained. This is going to be freeze. This is going to be freeze. This particular weight is going to be trained. Now after the training, it will be merged into the old weights. So that's a whole sort of a idea of the LoRa. We'll discuss it in a more detail in the upcoming session. So this delta W is called the patch, and this is only called the delta patch. Okay, and this is my LoRa weight. Now we no need to stack the LoRa weights. Okay, see, this is my W, the original weight. If we are doing a non-instructional training on the safe model, we'll get this W1, del W1. Then if we are doing the instruction tuning on top of the same model, then we are going to be attach this del W2. Then for the preference learning, again del W3. So we should not take this particular step, and this was the mistake even which I made in the previous solution. Okay, I will give you the correct approach, which approach basically you can follow for the LoRa. Okay, if you are using a same model again and again for the training, that how to use LoRa efficiently, it's very very important. Now what is the disadvantage of this thing? So the disadvantage is loss will be unstable, model will hallucinate, tuning will not be good, and the quality will degrade. Why it will degrade? Because loss will be unstable. We won't be able to figure out the loss properly, right? If we are having this kind of weight, if we are going to be create a stack of the LoRa, right? So what is the solution of it? So to use the LoRa in an efficient way, that's the solution. Let me show you how. So let's discuss how we can use LoRa in a better way. So if you will check PEFT, guys, so this PEFT is giving me two methods. One is get PEFT model. The second is PEFT model from pre-train. Okay, So when we have to use this get PEFT model, and when we have to use this particular method, so definitely we'll be talking about it. Now here we have a get PEFT model, so it creates a new LoRa during the training, means the new LoRa patch, the delta patch which I showed you. Now this PEFT model dot from pre-train, now what it does, so it load a already trained LoRa model, okay, for the inference or for the further training, right? So we are going to use this particular method for loading the previous LoRa weights, for the for loading the previous trained LoRa model, and then on top of it only we are going to perform the fine tuning, okay? But the way is going to be a little different. See over here, observe over here what we are doing. So we have a LoRa configuration. So here I am writing task type is going to be causal LM, that is for the next token prediction, okay, for the language modeling. Then there is the rank of the LoRa. R is representing the rank. LoRa alpha is one of the parameter. LoRa dropout, okay, one of the parameter. It's a hyperparameter. You can keep any sort of a value of it just to test your output. Means just to check what impact it is having on the final output. Then which like module we are targeting in the attention layer. So we are mentioning that part over here, and bias is equal to none. So this is what this one LoRa configuration. Now what we were doing, guys, in the previous class, and even if I didn't find out the current approach, then what we would be doing, let me explain you that first, okay, then we'll come to the correct approach. So we are having this method get PET model. So we are simply passing this instruction model, okay, and then we are passing this LoRa configuration. So we were thinking, okay, now we will get a model which we can tune further. But guys, this is a wrong approach. Now what we are doing over here, we are having the instruction model, and on top of it we are going to be connect the LoRa stack, okay? So the stack of the LoRa again and again, okay, on a like same model which we are training on a different phases to append the LoRa, okay, to create a LoRa stack. It is not a good practice, okay? So what is the correct approach? Let me tell you that. So first what we'll do, guys, we will load the base model. So here is my base model, okay. I'm not going to take this particular step. I'm just going to be comment it out, means directly I'm not going to be take a model, means directly see here I'm giving my instruction model which I loaded earlier from the zip, okay, and here I'm attaching the LoRa stack, and then I'm getting this PEFT model LoRa, but I'm not going to perform this thing because this is not a correct approach. So what I will do, guys, so first I will load my base model, okay. Inside this particular variable I was having the base model. So let me show you this base model which was there. So here is the base model, okay. So we are able to load the base model. I got it inside this variable. Now in the second step, what I will do, using this method PEFT model dot from pre-train, okay, I'm passing this model, my base model, and I'm passing my instruction checkpoint, means this instruction model, okay, this particular model. Now after that what I will do, so after loading this thing I will get my model, okay. So this model, this base model, basically it is connecting to the instruction checkpoint, right? Now what I will do, I will merge it, okay, merge and unload the weight, means I was having the base model, on top of it I will keep the LoRa weights, I will merge both weight, okay, and after that I will get my model. So here is my model. Now what I will do, on top of this model only I will connect the LoRa stack. So here is get PEFT model, I am passing my model, and then I am passing the LoRa configuration, right? So just check out all the thing. It is very much important, guys, very important. See over here. So what I'm trying to say, just focus over here just for one more minute, okay, guys. So we are having the base model, we perform the non-instruction fine tuning, okay, after the LoRa, and we got the non-instruction model. Then again we were having the instruction data, we perform the instruction tuning, and we got the instruction model, okay. Now this two thing, this non-instruction model I did with the LoRa, instruction fine tuning, again I have loaded this non-instruction model and I attached with the LoRa, and then again I perform the trading, and then now the same thing I'm going to do with the preference model also. But guys, this is the wrong technique, okay, to create a LoRa stack like this, which I explain over here. It is not a good thing. Why? Because we might get this kind of issues. So what is the best approach? The best approach is first, guys, see here is my basically this instruction model, this one, this is my instruction model checkpoint 3, okay, which I already trained, right? So what I'm doing over here, see, just focus for one more minute. So here basically what we have a LoRa configuration, that is fine. Now I'm not going to be like pass this instruction model, and we are going to be create a LoRA again on top of it, and then I'm calling it is my preference model which I'm going to tune further. No. So here I'm taking a base model. So I'm loading it. Now after that we are going to be connected to the instruction checkpoint. Okay. Now after that I'm calling this method merge and unload. So merge and unload, what it will do, it will merge model, my freeze model, as well as the instruction LoRA. Okay. Then on top of it I will create the LoRA patch. Now this particular patch is going to be trained. Okay. Now this particular patch is going to be trained. So this model which I got, a PEP preference model LoRA. Okay. After, see, this is my method get PEP model. I'm passing my model. I'm passing my LoRA configuration. Now I will get the delta patch. Okay. I will get the LoRA patch delta, the delta, right? Now that particular so I'm keeping it over here inside this particular variable. Now I will be training this model on top of my preference data set, right? So here I created one table also, non-instruction base LoRA, it is correct, instruction base plus merge, okay, stage 1 LoRA, then new LoRA, this is the correct approach. Directly LoRA on LoRA, it is not a correct approach. Now preference base, so base model, then merge stage 2 LoRA, then plus new LoRA, this is the correct approach. LoRA on LoRA on LoRA, this is not a correct approach. I think now you got the complete LoRA. So let's train my model. So here I am going to be write bits and biases disable true, and don't want to be capture any sort of a matrix. So here guys, I'm going to be define my DPO trainer from the TRL. So TRL is giving me these classes, DPO trainer and the DPO config. So yeah, this is fine. Now what I will do, I will create a object of this class DPO basically config. Now here I'm writing a directory in which directory, in whatever directory I want to be save my model. Here I have a learning rate and then I have train batches. Okay, gradient accumulation is step, right? At how many steps we are going to be accumulate the gradient value. Number of training epoch, how many, for how many epoch you want to be running, beta value, report to none. I don't want to report on any basically platform. Okay. So here also I did that same thing, and you can mention this parameter also. Logging directly none. As of now I don't want to be log anything. Loss type is sigmoid. Okay, we'll collect the will calculate the loss with this particular function. Remove unused column. Okay, false. I'm not going to be remove any column as of now. I know guys, you get the little difficulty while you go through with this all this particular parameter. We have so many parameter. If you will hover the mouse over here, you will get maybe. So we have so many parameter over here, maybe hundreds of parameters. So don't worry guys, it is my responsibility to teach you everything. I will create a proper video on top of each and every parameter of these classes. Okay, it is my promise. So let me take this DPO argument. Now here I am defining the DPO trainer. There I am passing my model. Okay, which the model basically here you can see this particular model, this one, preference model LoRA. Now how I got this model? So I was having the base model. Okay, on top of it I appended this instruction checkpoint. I merged both the weights. Now on top of this particular model, on top of this particular weights, okay, this particular model, I attached the this like LoRA patch. Okay, and then I got this model, and further I'm going to train it now. Okay, now here is my model and reference model. I'm not passing any reference model, otherwise I can pass the reference model over here. That is also one of the facility. Okay, argument, so DPO argument, this particular argument which I defined over here. Now after that guys, training data set, so data set which I loaded, okay, from the CSV, this particular CSV, this I shown you. Okay, only 5 data points, you can keep as many as. Then here processing class, that is tokenizer. Okay, so if I run this trainer, so see, it is saying preference model is not defined. So let me run it first. Okay, I got this one, this is fine, this is perfect. DPO argument is also fine, DPO trainer is also perfect. Now trainer.train. Now guys, this is my final step for training the model. So trainer.train, and yes, my model is getting trained. It will take time guys if we have a huge model and the very huge data set. As of now it is a quick, because we have a very small model, not very small guys, we have a small model with a very small data set, and my epoch is 1, and I kept the parameters in such a way it won't take much time, just to show you guys, just to show you. But in a real time you will be doing it with a huge amount of data, so it will take maybe days. Okay, now here it is just testing. So testing with a non-instruction model. Okay, so here is my question. Explain how metformin works in the human body and why some research believe it could have benefits beyond diabetes treatment. So guys, if I will test this question with my different model. Okay, so let me test for two model, instruction and the preference. You can test from your end this one, non-instruction one. Okay, so this is my question, guys. Now what I'm doing, so here is my testing with the instruction fine-tune model. So this was my checkpoint. Okay, instruction one. Now I'm going to be load this model. See, instruction model would be here. I'm going to tokenize this question. Okay, and then I'm going to generate a output, and then here will be my final output. So let's see what will be my final output. Guys, we'll compare the output. Okay, we'll compare the output of the instruction model as well as the preference model. Let's see the difference, whether we are getting some good terminology, something like that, right? So it is saying question is not defined. Let me execute it. Okay, so here we have a question. Now model is there, input tokenizer is ready. Okay, now here is my output, and then I will be getting the final output. So let it complete, and yeah, I will get the final output, guys. Just a second, it takes some time. Yeah, so this is the output. Now see, guys, explain how metformin disease is that. Now see, this is the answer. Crohn disease, inflammation, bowel disease. I don't know this is correct or not. You should check it out, right? But guys, there's some redundancy in the output because I did the mistake in the previous training. Okay, I will come to that just a second. Now here is my model path. This is my LoRA mod. This one preference based model. Okay, see here I saved that model inside this folder, tiny llama preference alignment. See, there's a folder. Okay, now what I'm doing, I'm going to be load my model path is here. I'm going to be load my model. Now I'm going to be connect with the CUDA, okay, to the GPU. Then guys, I'm going to be tokenize the question. Okay, I will be getting inside the input. Now this input I'm passing to my model. Okay, preference alignment model for the final generation. Now let's see the final output. So let's see what I will be getting over here. So it takes time. The output generation might take time. Let it complete. It depends on the infra also. If you have a good GPU, good infra. Now see, guys, explain how metformin works in a human body. This is that. Now see, metformin common diabetes drug, treat 2 type. So see, guys, you can clearly see the difference. So difference between this normal output from the instruction tuning and the output from the output after the alignment. Okay, so guys, you can make a difference over here. Means you have trained a model on top of the instruction data. That is fine, that is completely fine, I'm not denying that. But if you want to more enhance on the human preferences, you can take one more step, like this chat gpt have done. If you're training your model from scratch, this will be very helpful. Now I was saying, guys, I have done one mistake. So the mistake basically I rectified over here. If you will go and check with the instruction tuning, so I written that code over here. You can now execute this file, and in whatever way I have explained you this LoRa stack over here. Okay, so see, this I'm not going to be follow now. Means I will not append LoRa. First I will merge the weight, and then only I will append the LoRa patch. Okay, so I kept the code over here. Let me show you where it is. This one. Now let's okay, I think it will be the below one. So see, guys, this one. Okay, I kept the complete code. You can go through with it, you can run it, and then you can train your model. So fine, guys, this is it for this particular video. In the next video I will come up with some different framework, okay, to teach you this fine tuning. Yeah, so thank you, guys, thank you for watching it. If you haven't subscribed my YouTube channel, please subscribe. This kind of content takes very much effort, guys, to research and all, and then record. So please respect for all those things and subscribe the channel, because see, guys, it is free for you, I know, but it is very important for me. Okay, your subscribe, your like, your support, everything. So fine, I'll see you in the next video. Thank you, bye bye, take care.